Good morning, everyone. Welcome back to this hands-on workshop on Science DMZ and P4-DPDK. We are starting our day number 2 of this workshop, and we will be talking a lot about P4-DPDK data plane development kit. First, I will start with some updates in the website. In the chat window, you have the website. It's where we place all the information about the website, presentations, and also the video of day number 1. In day number 1, we cover Science DMZ, data transfers, high speed, BGP, and other topics. A reminder, we would really appreciate if you attended day number 1, and if you didn't do so, to give us a feedback so that we can improve and continue offering these workshops. For today, day number 2, we will focus, as we said before, P4, this programming language that is used for describing packet processing, not only on switches, but also in the user space, and that's what we're going to be talking today. We will have an introduction, fundamentals of P4. If you never saw P4, we will discuss that, the same with DPDK. And then demos, what can be done in the user space with P4. We have created a lab library. Samia, who is a PhD student here at USC, and Eli, a faculty at USC, they are leading this new library on P4 and DPDK. Again, DPDK is to use in the user space. And then we'll have, I guess, Andy Fingerhead from Cisco, a lot of knowledge about smart NICs and how P4 plays a role on smart NICs, how to program those smart NICs, architecture, etc. And we will have a second lab on match action tables using the portable NIC architecture, how to program these smart NICs with P4. And that will conclude our day number 2. So let's start right away. I will start by briefly introducing Eli. Eli was already helping day number 1. He will be leading this day on P4-DPDK. Eli is an assistant professor here at the University of South Carolina. He did a lot of work on P4 when he was a PhD student. And he's the leader on these topics, P4-DPDK. Eli, welcome, and feel free to share your screen.
Thank you, Dr. Jorge, and welcome everyone. I will start right away by sharing my screen. Can you see my screen?
Yes.
All right, thank you. So again, welcome everyone. Thank you for joining on this second day of the workshop. In this set of slides, I will give a brief overview introduction on DPDK and why we need P4 for DPDK. We're gonna go a little bit with the background on packet processing in general in Linux systems, so that we can motivate why DPDK is essential, and then why P4-DPDK would help a lot. All right, so let's start first with the packet processing on handhosts. What is the life cycle of a packet coming to the server? So on the operating system, we have the user space and we have the kernel space. The user space is where your application would be running. And in the kernel space, we have a bunch of drivers that would help us with the controlling with the hardware. So the network interface card driver, initially it will pre-allocate the kernel memory buffers in the kernel space. So this is where the packets would be stored. It also pre-allocates the transmit and receive ring buffers in the memory. So TX here for transmit and RX for receive. So what do these rings contain? These are basically circle queues. So whenever we receive a packet, we'll be inserting it and then incrementing by one all the way till we fill the ring. Now, these rings will contain pointers to the packet within the memory buffers. And they contain other metadata such as the packet length. And so whenever a packet arrives to the network interface card, which is the NIC here, first it will be stored in a hardware receive queue. And then the network interface card will copy that packet to the memory. And it uses a technique called DMA, or direct memory access. The idea here is to not involve the CPU by doing this copy so that we can get better performance. After that, the network interface card will generate an interrupt. It will trigger an interrupt just to tell the NIC driver that now we have packets available in the ring, in the queue, that are ready to be processed. Okay, so in summary, the packet is received, it's copied to the memory, an interrupt is generated, and then the NIC driver will continue from there. So when we have this interrupt happening, what would create is basically the CPU that is busy running some process in the user space is going to be paused. And then we're going to switch from the user space to the kernel space. So we will do here a context switch. And this operation is costly, so it takes some time to perform that. After that, the CPU will acknowledge this interrupt and will schedule the bottom half processing. It will go back to the user space because always the application in the user space will have more priority. So it will continue, it will resume executing what was in the user space. Then when it's free, it will switch back to the kernel space from the user space. And from there, it would allocate a data structure for each of the packets. Okay. And after that, it will remove the Ethernet header and pass the network to the next step, which is processing the IP header. Okay. And this step will be executed for all the packets in the buffer. Okay. So again, when we have an interrupt, we saw that there are multiple context switches, meaning that we move from user space to kernel space and vice versa. And this operation is costly. And also there are other costly operations like dynamically allocating the memory for all of these packets coming. And after that, we have to continue with the remaining packet processing, which is parsing the IP header, and then later on the layer 4 TCP, and so on. So as you can see, all of these happen for every packet. And that's a lot of time that's being spent just to process the packet. There are some optimization in the Linux kernel so that you don't do it for every single packet, but it's still, all of these will create overheads that would prevent us from achieving high rates. So in summary, what are these overheads? We have too many context switches, meaning that we move from kernel space to user space and from user space to kernel space. That will also pollute the CPU cache. Second, we have interrupts that are generated for every packet that would cause the CPU to pause and then move and then try to schedule the packet processing. We have dynamic allocation of the packet data structure. And we have also the copying of packets from the kernel space to the user space, to the application, so that that packet is going to be consumed eventually. Okay, so that's different from the DMA that was from the network interface card to the kernel space. This is an additional copy from the kernel to the user space memory. So why is this important? Because if we look at this table here, we can see here on the first column the link capacity. Start with 10 megabits all the way to 100 gigabits per second. And let's assume that our packets are 64 bytes, small packets, right? So the time budget per packet to achieve the line rate, okay, is listed here. So we can see that with 10 and 100 megabits per second, that's not a big deal because we have enough time for every packet to be spent in the kernel, right, and to be processed. But when we start going to higher rates, like 10 gigabits and 100 gigabits per second, we see that we have few nanoseconds of time budget for that packet to be processed. Now, with all the overheads that we discussed here, this is already passing those few nanoseconds by a lot. And that really prevents us with the current architecture of packet processing in service. It prevents us from reaching high rates. Okay. Now, this is really, we are looking only at 64 bytes packets. Now, in reality, you have 1500 bytes, you have some packets in the middle. So they don't always have to be that small. But if we're just considering smaller packets, which some workload can have a lot of small packets, we're going to end up not achieving the line rate. So how can we solve that? One approach, and there are other approaches as well, but one of the more common approaches to solve these overhead is to bypass the kernel. So what is the idea here? We would have a network interface card, right, that supports DPDK. DPDK stands for Data Plane Development Kit. And the idea here is to try to bypass the kernel space by having the packets being pulled to the application directly. So on the user space, we have some drivers. We call them PMD, poll mode driver. And that driver will be basically having an infinite loop, waiting for packets to arrive at the NIC, and then it will retrieve all these packets by batches. So we have a bunch of packets coming, we immediately copy them, and we don't involve the CPU. We use direct memory access too. So by doing that, we have a lot of advantages. First, we don't have anymore the interrupts that are creating the overhead in the kernel. Second, we are bypassing the kernel altogether. We are copying one time directly. We use DMA, we copy the packets directly to the user space. And basically, with all of these, we will have much better performance. We were not going to be waiting a lot of time for every packet that comes there. So in summary, DPDK would allow us to write at the user space the packet processing logic, right? And it has some drivers that would allow us to extract or get all these packets from the NIC, process these packets, and then send them back or drop them or do whatever we want with them. Okay. So DPDK is based on C. So you write a C program, you import some libraries, and then once you start your application, you would have a loop. That loop will be accepting the packets, and then you will be processing the packets on batches. Okay, so the whole idea is to try to minimize these interrupts so that we can get better performance. Now, this is good, but how can we even make it faster? How can we scale? So at the end, the packets that are going from the NIC, they will be processed by the CPU on the user space. And if we have a single CPU, that CPU might become the bottleneck, especially if we want to achieve high-speed packet processing. So modern network interface cards, they have, they implement what we call a receipt-side scaling, which is a technique that is implemented in the hardware. So you have a hardware there within the NIC that you have. There's a hashing module, and there are a bunch of queues. Can be 4, 8, it depends on the NIC model that you have. All of these are hardware queues. And the idea here, whenever a packet is received from the network, we would hash the 5-tuple, the flow information from that packet, and that would take us to one of the available queues there. Okay. Now, each of these queues would be basically consumed or utilized by one of the CPUs. So let's say I have 8 queues, I can have 8 CPU cores, right? Each CPU core will be just processing packet coming from a single physical queue. So with that, what you can do basically, your DPDK program or the packet processing that you have, you can scale it to run on multiple cores. And that would allow us to even have better performance. And not only that, you can have different type of pipelines of packet execution on these CPU cores. You don't have to have the same one on all the CPU cores. So all of these are techniques, again, just to make the packet processing faster. All right. Now, let's take a look a little bit on some numbers, right, when we use DPDK. So what you see here, this is an example of a layer 3 forwarding implemented in DPDK. So in this application, basically, when we receive a packet, we will parse the Ethernet, we will parse the IP headers, we inspect the destination IP, and then we take an action, whether we want to forward the packet or we want to drop it. So it's basically like a layer 3 router. Okay, so the results that you see here is we have 64 packets, right? So on the x-axis here, you can see the size. So 64 byte, 128 to 56, all the way to 1500, 18 bytes. And on the y-axis, you have the frame rate. So how many million packets per second we are processing. Okay, and here we are using the network interface cards from Mellanox or NVIDIA. And you can see here, this is a report here. And typically, every time they launch a new version of DPDK, all the vendors would create a report, and then they will post it on the DPDK website so that they can basically show that their NIC is able to basically achieve those rates. So again, we are running here layer 3 forward. And what you can see here is that with 64 byte size of frames or packets, we are able to get 148.81 million packets per second. And basically, what you can see here on the this gray line, this is the line rate. So this is showing us that regardless of the packet size or the frame size, we are achieving line rate. And here we are using 12 CPU cores. So with that much CPU cores that you have, right, and with DPDK enabled, you can write a custom packet processing, like enabling, layer 3 forwarding, or you can do more interesting stuff, more innovative stuff, and you are still achieving these speeds, 100 gigabits per second. This is the type of numbers that you would never see by just using the kernel and following the typical life cycle of a packet. All right. Now, if you are interested, you can go to the DPDK website and you will see reports for other type of experiments. And you can also see different from different vendors. We have Intel and you have other NIC vendors that you can also see the numbers there. And also there are other type of tests that are found in each of these reports. All right, so DPDK is great. We are getting very good performance. So what is the problem here? Writing an application in DPDK can be a little bit complex. You would need to know a lot of background in C and DPDK libraries, which, I mean, it's not that bad because a lot of people know C. But if you're coming from more the networking background where you just simply configure and express what you need in a very, very high level, that can be challenging for you to create your own custom packet processing. For example, to implement a simple software switch, you would require millions of lines of code in C with DPDK. And because the program can get very large, it's very hard to add new features to that large code. So it becomes more and more challenging. So what can we do to make this a little bit easier? So recently, P4, which is a programming language, a high-level programming language, emerged, and it's a domain-specific language to define packet processing. So what do we mean by that? Historically, network devices were all proprietary and closed. So you would buy, let's say, your switch from a vendor. That switch would have fixed function data plane. In the past 10 years, there was kind of a new trend where now the data plane is becoming programmable. Data plane of these switches, this is usually where you are doing all the packet processing at high speed rates, right? So P4 was created as a language so that we can define the packet processing in the data plane. So it started first with these programmable switches, programmable data plane switches, P4 switches. All of these are names that are used for these devices. And just to give an example so that you relate, if you've ever heard of Intel Tofino or Barefoot Tofino, these are programmable data plane devices. So the P4 was initially built to program these devices. But because of its ease of use and its expressiveness, it became a language that can be used to really define packet processing in general, and not specifically for those data plane programmable switches. So what do you do with a P4 with P4? What can you do there? So first you write a P4 program. Again, this is a very simple language, much shorter than what you would do with DPDK. You define the packet processing, you define the headers that you would like to parse. It's all up to you. And you implement an application. Let's say you want to implement a packet classifier and then do layer 3 routing and then run an access control list. So you would express all of this in P4. Then the P4 program will be fed into a compiler, a P4 compiler, that will generate a target-specific binary file that can be loaded. So for example, if you have a switch, you write a P4 program, you pass it to the compiler will generate a binary file that you can load into the switch, okay? At the same time, it will generate control plane kind of metadata or specifications that you can use to populate tables at runtime, to manipulate registers, to be able to really control that data plane that you have. Okay, so you write the P4 program, you generate the binary, you push it to the hardware, and then you have some Python or C or C++ basically program running in the user space, and then you will use that to populate the data plane device, the data plane of the device. Now, I just gave you an example on how we are using it for switches, but think of this target here. It can be basically a network interface card, a smart NIC. The newer generation of NICs are programmable. They have a pipeline that can be programmed. Or also think about it as the CPU, right? Which is the focus of this talk here in this workshop. So you write P4, you generate some code, and that code will be loaded into CPU so that you process the packets there. Okay? And P4 is an open source language. It's available. I mean, it's very well maintained. There's a lot of new patches and updates pretty much on a daily basis. And it's designed so that the back end is separate from the front end. So the back end, let's say there's a new device that is P4 compatible, you will create your back end so that it complies with the compiler, and then you'll be able to use the P4 program to generate the binary for your device. Okay, if you visit the GitHub repository of the P4 compiler, you would see in the backend there is a lot of different backends supported now. Okay, so when they designed the P4 language, again, it was first with these switches, and those switches have very limited memory, very limited processing in the hardware. So the idea was to create some model, and that model would allow us to define what packet processing would look like, right? So this is kind of an abstract model, but it's very common regardless of where you're gonna be programming your target. What do that model have? So first, this is called PISA, or Protocol Independent Switch Architecture. The idea here is that you have a parser, and here is where you parse the packet. And this is completely programmable. So the device would not understand what IP is, right? Or what TCP is. It's up to you as a developer to say, well, this is how the IP header, IPv4 header would look like. This is how the IPv6 header look like. This is what TCP look like. And then you would say, if you see this field within the header, you jump to that state, meaning now you are parsing a different protocol. So it's very programmable, and as a device, it would not understand the standards. It's up to you to define them. So this is what the programmable parser would do. You would start by parsing your packet. Once you have the headers available to you, you will move to the pipeline. And there you would have multiple stages, and each stage would have memory and would have some processing there, right? You would do match action processing. Think of it as a table. A table has a key and has entries. You receive your packet, you decide on what you want to match on, you perform some action. Maybe you want to, let's say, decrement the TTL of the IPv4 header, or I don't know, you want to modify some of the fields there. So here is where you do your custom packet processing in the pipeline, right? So once the packet is parsed, you do all these transformations. You go from one stage to another. And you can see here we have multiple units within this stage so that we can use parallelism. And that's why, I mean, it's very important to do that so that we can get high traffic rates. So the headers will go through many transformations depending on how many stages and what your program would look like. And finally, you would have these headers ready to be transmitted to the wire, right? So here you have a deparser, and that's also programmable. You can say something like, for this packet, I don't want to emit, let's say, the TCP. I want to emit a custom header on top of IP. That's doable. That's up to you to define it. Okay? So with that being said, the P4 program looks something like this. It's very simple. You say, well, that's my parser. I'm parsing here the Ethernet, so that's a state. After parsing the Ethernet header, I would need to look at a field, which is the ether type. And based on the value of that ether type field in the header, I can know which next state to parse. So if it is 800, we go to parse IPv4. You will have another state for parse IPv4, and then you can basically parse the IPv4 and then go for TCP or UDP or whatever protocol that you would like. But you can see here, I mean, the type of coding that you do in this language is very specific to packet processing. You have a parser, you have match action pipeline, and then you have the parser. It's not like you have a general language like C where you have to do all the coding to make it tailored to packet processing. Okay, and this has some advantages because it would make the code much smaller than writing, a fully fledged C code to do a very simple packet processing. Now, in the match action pipeline, you would have tables, you would have actions, you would have if statements, you would have bit manipulation. You can do shifting, you can do plus, minus. You can also store information in registers. You can have counters, you can have meters. So a lot of elements are available to you here in the match action pipeline so that you can do processing on these packets. And because also enable stateful processing, you can store information so that you can retrieve that information for other packets. And each packet would have some metadata with it so that you can basically move from one stage to another and then use that metadata throughout the lifecycle of the packet within the device. Okay, so what we need to understand from all of this slide basically is that the P4 program looks very simple. I mean, you just express what you want in terms of packet processing, and it's mapped to the components within the architecture. We saw the PISA architecture, which is really just a model, but devices or targets, they would create their own architecture that follows these open source ones like the PISA one. Okay, and later on we will see in the talk that there's an architecture called PNA, Portable NIC architecture, which is a variation of the PISA, right? But it's more tailored towards network interface cards and end hosts. And this is what we're going to be using when we program the PDK target. Okay. So why P4 for CPU? We said that the packet processing on the server is very similar to a switch pipeline. So you receive the packet, it must be parsed. You need to do some matching and then perform actions on the packet. And then the packet is sent to the network or sent to the host if it is on the NIC. Another reason is that the description of a P4 data plane is short, right? So there is a well-known program called switch.p4, which is a P4 program that contains all the functions of a typical data center switch. It has around 5,000 lines of code in P4. That same program, if you want to write it in C with DPDK, it has millions of lines of codes. You see here are some also some attack defenses that are implemented in DPDK and in P4. P4 is much smaller, even though these numbers, they look a little bit small here for DPDK, but in reality, when you start adding other functions, these numbers start growing really rapidly. Okay, so much shorter code. And of course, with the high-level abstraction of P4, it allows us to simplify the development of these custom packet processing. And it would allow us to add some features very easily. Let's say I have my P4 program and I decided, well, I want to parse these new packets and have this custom packet processing. It's much easier to add it over adding it on a very large code. So the idea here is we want to combine P4 and DPDK, right? Because P4 is very good in expressing packet processing, right? And it's very high level and easy to use. And DPDK has the performance capabilities, the benefits of having our program run at line rate. So P4-DPDK is an initiative that was designed to do exactly that. So you have a P4 program, right? We want to load that P4 program into a CPU target. I'm not running it on a switch with an ASIC or an FPGA or anything like that. I just want to run it on the general purpose CPU. And you would pass that P4 program to a compiler, P4C compiler, using the DPDK backend. So this compiler with the DPDK backend will generate a specification file, .spec file. And that .spec file is basically, if we will see it later on in the lab, but if you look at it, it's very similar to a kind of like how assembly is like, right? So you have a move instruction, then you have apply for something else. So it's kind of a instruction set, right? It's like a virtual machine there that would be consumed by the DPDK pipeline library. So there's a library in DPDK that is designed just to implement pipelines. And the pipeline here is very similar to what we talked before. You have match and action. So you have your receive ports, your transmit ports, packet comes, you have matching, you apply some actions, you can have multiple tables, and then you send the packet out. And because of the nature of this pipeline and the way it is, so they said, well, the P4 program at the end, everything can be translated to match and action, as we saw in the architecture. So the idea here is to have this specification file be mapped to these tables using the pipeline library of DPDK. And that will generate us a C code, which will use the C compiler, which we typically use to compile our DPDK code. And that will create a shared object that now we can load. So really, you are now using DPDK, you are getting the performance of DPDK, but also you are getting the ease of use and the expressiveness of P4. Okay. This project started with Intel and it's open source now. So there are some updates happening there. And now it's being used a lot actually in a project called IPDK, which is an initiative to make standardized APIs to program smart NICs. So they use this as a kind of like a way to test while they're developing this IPDK. Now, keep in mind that this is not a simulator. If you know a little bit of P4, you might have heard of BMV2, the behavioral model. This is not like BMV2. The goal here is to enable performance. BMV2, you can get maybe 1 gigabits per second, best case scenario. With P4-DPDK, you can get 100 gigabits per second. It's designed to use DPDK. So what are some supported features of P4-DPDK? I took this slide from Christian here, who is very active with the development of DPDK and P4-DPDK. So you can see here, there's a lot of features supported. Parsing headers, metadata, the actions, the pipeline, all of these are there. You have counters and registers and meters. They are all supported, meaning that you can also store information so that you can use them across multiple packets in the pipeline. Some newer features, we can do longest prefix matching, LPM. There's the add-on miss table. We're going to see an example of that later on in the lab, that essentially allow you to populate the table from the data plane. That's something that wasn't available with P4 switches. Packet mirroring, P4 runtime support, recirculation. a lot of optimization to make it a little bit also more performant. The PNA architecture, so we're gonna have a talk on PNA later today, but this is what basically the architecture that maps to the PISA. And also, this is also new, there's a support for software-based NICs. So in order to use P4-DPDK, you don't have to really have that NVIDIA NIC or Intel NIC, have a physical NIC with you. It's possible to use a virtual interface, a software NIC in the kernel, just to be able to learn. I mean, it's not going to give you high performance. We're going to see later on in the lab that it's not the best way to do it if you want to deploy it in a production network, but this is just for teaching. And for the labs, you're going to be using software-based NICs. So you will not see the performance as you are writing them now in the pod. However, if you have a DPDK compatible NIC, the same code, the same steps you will use, and then you will get the high performance. Okay, we're just using software NICs here just to be able to scale and have everyone a pod so that they can run the experiment simultaneously. Okay, there are some more features to be available in the future. For example, cryptography and IPsec. This portable NIC architecture that's being used now with smart NICs and with DPDK, a lot of time it can be used to basically do some operations related to IPsec, like decrypting the payload and adding the IPsec header and so on. So because these are some of the features that are common in the server or in the NICs, they added it as part of the language. So it's not supported yet, but it will be in the future. And there are other things that they are working on to make them available. So as we said before, it's very nice for expressing packet processing logic. Now it's being used, as we said, not only for switches, but for end host stacks. What we are doing is using it for programming the user space, the PDK, but there's also other projects for programming in the kernel space. So if you've heard of eBPF or XTP, these are technologies running in the kernel. So you can write also P4 program and generate the corresponding code for them. It's also being used for software switches, right? Like Open vSwitch. And with smart NICs, these are the new NICs that come with a programmable pipeline. P4 now can be used to generate FPGA code. There's a project P4 FPGA. So you write P4 code, you have FPGA design, and then it will be loaded into the smart NIC. Can be with ASIC. Different vendors have different options. Some vendors are going more over the ASIC path, others more FPGA. Others also system on chip. You have CPU cores within the smart NIC that can be also programmable. So it's becoming more and more popular, not only for switches, which initially was designed to target. And there's a vision now, it's a common vision in the community to make all the pipeline, all the paths, end-to-end path programmable, right? And P4 is a great option to do that, right? Because now you can use P4 to program the user space with DPDK, can use it to program XDP. The NIC itself is programmable, the smart NIC can have OVS switch, a software switch, use P4 to it as well. P4 switches in the middle, they all have programmable pipelines, all the way to the other end of the session where you can also have a P4 program. Now, that doesn't mean that if you want to use P4, everything should be P4 programmable. This is just kind of a futuristic or ambitious vision that everything will become programmable, and the network is no longer just being used to forward packets and do minimal packet processing, but it's more of you have a custom application, that application you map it to different parts of your path, right? And all of that is expressed in P4, and you can use fine-grained telemetry information, like in-band network telemetry, to improve the network. So in conclusion, packet processing stack on the server has a lot of overheads. You have context switching, interrupts, packet copying. All of those make the packet stay for a longer time in the server before it's consumed by the application. And all of these overheads would not allow you to get high rates, especially with small packet sizes. Now with the DPDK, we minimize these overheads by bypassing the kernel, so we don't have any more interrupts, and the packet copying is done without CPU intervention, no more context switching. So we try to solve these overheads. We can leverage multi-core CPUs. If you have multiple cores on your server, you can leverage them all and have them pinned just to be able to execute these packet processing. P4-DPDK, so it's a project that allows us to write P4 and then leverage the performance of DPDK. And eventually, I mean, P4 is being used with multiple devices, and eventually there might be some shift in the networking industry where everything is programmable, and P4 can be a great option to achieve that vision. All right. So is there any question before we move to the next part? So I see a question in the chat. So in DPDK with RSS, the bottleneck, let me see. In DPDK with RSS, the bottleneck would be CPU core assigned to a given flow. Pretty much, yes. If you are using a single core, yes, that would be become the bottleneck. I will show you in the next part of this presentation a demo that we did where we used multiple CPU cores and we got much better performance. So yeah, using multiple cores, you would see the improvements. Another questions, you show the comparison of number of LOCs for various defenses in P4 versus DPDK. I took a quick look at the reference YouTube videos. Is it correct to assume that the DPDK column here is showing the number of LOC that would come out of the P4-DPDK translator versus what a human might be able to write? Could it perhaps be lower with more effort? Definitely, I think these numbers, let me just go here. Yeah, I think here I might have to update this. This might be a different reference. But this is a paper, I think it's called Poseidon with P4. It shows a table where it shows this information. But these are here if you are writing natively with C and DPDK. With the P4 one, that's just the P4 program. So you are really comparing C versus P4. That's not the P4-DPDK here. I hope that answers the question. If not, just let me know.
I have a quick question. Great. I don't know whether you can hear me.
Yes, yeah, we can hear you.
So I'm curious about how DPDK compares with RDMA in the context of IOPS heavy workload. And when in slide 19, when you were showing the numbers, seems that you use the ConnectX-6 in the Ethernet mode. Is that right?
Yeah. So this one here, yes, we are using ConnectX-6, 100 gigabits per second, each port on it. So if you go to that report, I will just open it really quickly. I mean, there's a lot of details there so that you can see exactly, or if you want to reproduce those results. It can be hard because they use a hardware graphic generator, but it's possible, and they have all the options there. You see here. And that's, by the way, that's another thing that is a little bit a limitation in DPDK is that it has a lot of tuning that has to be done. So, for example, NUMA tuning, huge pages, CPU pinning, all of these stuff you need to be very familiar with so that you can get the most out of it. Now, it doesn't always have to be the case. Most of the time, you get much better performance, even if you don't do proper tuning. But yeah, all the details for that test are listed here. By the way, yeah, sure, go ahead.
But how does it compare with the RDMA protocol?
Yeah, so with RDMA, I mean, there are some similarities in the sense that you are using the direct memory access, right? Now with DPDK, it's used to process packets, right? So you receive these packets in batches to the NIC, and they will all be pulled to the user space, and you will see all the packet there, right? Now with RDMA, it's a little bit different in the sense that you can use RDMA and have like write commands so that you write directly to the remote memory, but you are not really parsing the whole packet, right? So in RDMA, I mean, RDMA has a lot of different modes, so you can have it as a send receive, kind of like a conversation between the two servers, or it can be write only without notifying the server. So it has a lot of different modes, but the similarities is that both of them basically would be bypassing the CPU or the kernel in the DPDK one, but they would be doing direct memory access. The difference, again, is that with DPDK, you are receiving the packets and processing the whole packets, and you can get a batch of them. With RDMA, you can do so, maybe by writing in a lot of different cells in the memory, but then you would need maybe to inform the CPU that packets are available there or data is available in the memory so that it can go there and consume those. It can be with the interrupt or without interrupt.
So for smaller packets, it is in theory possible to get higher IOPS with DPDK over RDMA.
Yes, yeah. Let's see here. Yeah, I mean, here you see we got the line rate with these small packets. But one more thing that is very important, it depends on what the application is because you are running on CPU. So in these numbers we are showing with layer 3 forwarding, right? You just inspect the header and then you take an action, forward or drop. If you say, well, I want to implement something a little bit more complex there, you will see the numbers start going down. So it's unlike a P4 switch, if you're familiar with P4 switches that have an ASIC. And in the P4 switch, if your P4 code compiles, that it will run at line rate because it's ASIC at the end. Here it's different. The more you add to your program, the lower your performance going to be.
Gotcha. Thank you. And how can I implement DPDK, or is it part of the lab that you're going to show? I want to know how to install it, configure it, and so on.
Yeah. So regarding the configuration of DPDK, I mean, that's a very good question. It's a little bit hard, especially for someone just starting with it. But the problem, the other challenge with it is that it's very vendor specific. So let's say you have Mellanox NICs, ConnectX, or NVIDIA. You'll need to make sure to install the drivers for MLX5, which is the PMDs for the NVIDIA. But then if you are using an Intel NIC, it has a little bit some differences in the installation. It's not that hard, but you just need to know what your hardware is and then follow what's recommended by the vendor. Now in the lab, we're not going to show how you can install all of these. We're just going to show how you can start implementing your DPDK program in P4. We're not going to see the P4 code. If you are interested, let's say in like later on, if you want to do that on your own, there's also the VM available there, right? So you can download that and run it locally. And here you don't need the NIC because you are using the virtual NIC or using all virtual interfaces. But maybe in the future, maybe it's a good idea to add an additional lab to show how you can install the DPDK and make it work with some NICs available. I think that's a good thing to do moving forward because I see that issue all over the place. A lot of people have issues just compiling DPDK from source and make it work with the NIC.
Thank you. And I really appreciate in the beginning, you went into detail of packet processing by NIC. It made things much clearer for me. So I appreciate that. Thank you.
Yeah, I think this is kind of I mean, a lot of times when they start talking about DPDK, all they say is bypassing the kernel, but knowing really what's happening without DPDK would give insights on why DPDK is useful and now why P4 is useful. Okay, I see another question in the chat following on Chris' post. Is there a performance comparison, CPU usage throughput between P4-DPDK versus DPDK on the code? Yeah, that's a great question. I don't think there is one or there's a paper that does that. We just started working with P4-DPDK and DPDK. I mean, we're not experts, so we just started that, and this is something that we have in mind to try to benchmark basically the performance. But with that being said, one of the things that using P4-DPDK would make it more appealing is that really you don't need to import all the libraries and do all of the, have all the skeleton that you need for the typical DPDK code. What I mean by that is that with P4, let's say you don't want to parse IPv4, you don't have to add it in the headers, and that's not going to be included at all in your pipeline. So my guess is that you will see very similar, if not maybe better performance before DPDK. But that's something that we have to test. Is there any other question? All right. So we're a little bit over the time, but I will just show a very quick demo of what we worked on. This is the work primarily done by Samia. Samia is a PhD student, and she will be going over the next lab. And the idea here is to implement a heavy hitter detector using DPDK, using P4-DPDK actually. And I will just go over this short video here to explain what we've done here. All right, so what we have here is a topology consisting of 3 devices, and we are also using ConnectX-6. That's the same NIC that we saw the numbers for in the slides. The topology has in the middle here, we call it the heavy hitter detector. So this is where our P4 program will be running. We have another server that's just used to generate background traffic. We use a tool called PacketGen. PacketGen is powered by DPDK, and that allows you to customize what type of packets you want to send, and then it will send at 100 gigabits per second. And the other server here is going to be simulating or emulating a heavy hitter. So in other words, all the packets generated from the server on the right-hand side belong to the same flow, because we are assuming a heavy hitter is a set of packets that are all belonging to the same flow, right? Whereas on the left-hand side, the background traffic generator, they have different flows. So the packets are generated with different source IPs, destination IPs, source port, destination ports. Okay, and the heavy hitter, by default, is going to be reflecting all packets, meaning that if it receives a packet, it will forward it out of the same port it came from. And why we are doing this, it's because we want to see how many packets were really processed by the P4 program and reflected back. And by knowing that information, we can know how many packets were dropped. So we can see kind of what is the impact of that pipeline that we implemented on the packet loss. And we also keep track of the per flow packet count. Because of scalability issues, we cannot keep track of every single flow. So instead, we use a memory efficient data structure called count-min sketch. Count-min sketch would allow you to track the number of events, for example, in this case, the number of packets, in a scalable way by using a small memory footprint, but by sacrificing a little bit the accuracy and the number of packet estimation, right? So if your goal is to identify heavy hitter, you don't really care about the exact number of packets, but you want to really know that a lot of these packets have been generated by that flow. So you can use a data structure like count-min sketch to estimate that. So very simply, if we have a heavy hitter, right, we get the packet count. If it exceeds a threshold, we block it. So here, for example, we have 1 gigabits per second sent from the heavy hitter, and it was blocked. The 100 gigabits per second sent from the background traffic generator, those were processed. Now, the process is, as we said, we are using multiple CPU cores with RSS. So the packet comes, we hash it in the hardware, we assign it to a queue, and that queue is going to be sending the packet to the corresponding CPU core. In this case, we have eight CPU cores. And the P4 program is implemented in the P4, right? But we compile it all the way till we load it to the different CPU cores. And this is what we're going to see now in the lab, right? How we can compile from P4 to get that shared object and load it into the CPU core. This experiment, we tested it over Fabric. So yesterday we showed a demo over Fabric, if you were here. If not, Fabric is a test bed that is all across the country and has also connections to other countries. You can select the sites that you would like, right? And select the resources per site, connect the networks the way you want, and then you run the experiment. For this specific experiment, what we did was we just took one site in Seattle and we made sure that all of these servers are within one site so that we can just really have the results without having any other impact, like packet losses because of transmission issues or some buffer overflows, just to make sure it's all in one site, just to make the test a little bit cleaner. We did that. And with Fabric, they have NVIDIA SmartNICs Connect X6 available. So all you can do is say, I want server 1 in this site, server 2 in another site, or in the same site. And I want to add the Connect X to server 1, Connect X to server 2. Connect them. Now you have a 100 gig link between these two devices. And because those NICs are DPDK compatible, you can implement your code in P4 and then test it. Okay, so this is the topology again, so the three servers. So loading the pipeline is very simple. Once you have basically the P4 code written, you would need to compile it. That will generate a specification file, the spec file, right? And you can see here, there's a CLI file that has a bunch of instructions. We don't need to know all the details, but essentially what's happening here is that it's taking that specification file, generating the C code, and then we're building a shared object from that C code. And that shared object, now we are deploying it on 4 CPU cores. Okay, in our case here, we used 4 CPU cores. So now here we are seeing the traffic being generated. On the left-hand side, that's the background traffic. You have a range of flows that are being selected, whereas here you have a single flow. You see here, this is in megabits per second. You have the RX and TX. So we are sending a 99 gigabits per second. We are getting back very close value, 98. So we are pretty much getting 100 gigabits per second of packet being processed. Very small amount is being lost compared to the total volume. And this is not very accurate here in terms of, like if you want the exact numbers, because it's using sampling. So every second we are pulling to see how many packets are being received. So in reality, it might be processing really all the packets without any packet loss. And on the, remember that the program, the P4 program is reflecting the packet. So the background traffic are being sent to the pipeline and then they're coming back. That's why we are seeing the RX here. Which means that we are processing all these packets in the P4 program and then coming back to the server. Now here, when we sent from a single source, so the same flow, meaning that we're always gonna have the same source IP, destination IP, source port, destination port. You see that we are sending at 1 gigabits per second. The P4 program detected that, and now it's not reflecting the packets back to the server. And this is here a graph just showing the throughput in gigabits per second over time. You can see here approaching the line rate with the background traffic. It's not very visible, but you have dots here for the TX, and you have the solid line for the RX, just to see basically if we are receiving all the packets that we send. And these two here are overlapping, meaning that all of the send packet are being reflected. Whereas when we started here, the heavy hitter, right, we have a spike here because we are waiting to get to that threshold. Once we got to that threshold, we applied the rule to drop the packets. And now, even though the server is sending packets, they're not reflected back. So all of them are being processed correctly by the pipeline. And by the way, the code for that is available online. Ali, if you can add that information to the website at the bottom here, there's a GitHub repo for that if someone wants to, replay it on their own testbed. And I will also add, so we had a paper in this for this specific topic. And one of the other things that I thought is very interesting with P4-DPDK is that because you are not really implementing all the features, right? You are just specifically focusing on what you want there. You're gonna get better performance when you compare it against another DPDK based like firewall. For example, there's an open source intrusion detection and prevention system called Suricata. And Suricata has a DPDK version. So when you compile it, you can say, I want DPDK enabled. And what we did here, we compared the P4-DPDK heavy hitter versus the Suricata DPDK heavy hitter. And if you see with Suricata, we disabled all the other flows, all the other, signatures. So it's really just doing heavy hitter detection. So that we have apple-to-apple comparison. And here we have also the logic that we implemented to have Suricata just do that specific task. But if you look at the results, you will see that because of, you have a whole engine, the Suricata engine has a lot of features there, you will get a lot of packet losses. So each one of those lines is for a different packet size, right? And you can see here with the rates how the packet loss percent is increasing. So with small packet sizes, there's a lot of packet losses. With large packet sizes, a lot of packet losses. If you compare it to the one on the right-hand side, that's the P4-DPDK one, you'll see that the packet losses are much smaller. And same thing, when you compare it with real packet traces from, real networks, you will see that a lot of packets are being dropped. So just so that, we can get a lot of different packet sizes and not only focusing on the smaller packet sizes or the larger packet sizes. Okay. So in summary, even if other system is DPDK compatible, if they implemented a lot of things in it, they will see the downgrade in the performance. But with P4-DPDK, because you're only expressing what you want, you get this performance benefits. And finally, I just want to show here how the performance will increase with the number of CPU cores. And by the way, this is not very well tuned, so I'm sure we can get much better performance values. But you can see increasing the number of cores would basically increase the performance. All right, is there any question before we start with the lab? Okay, so I don't see any question. So the next activity for today is to do the first lab. And in this first lab, we're just gonna see how, if you have a P4 program, you wanna use P4-DPDK, what are the steps to do so? And this presentation is gonna be delivered by Samia. Again, Samia is a PhD student. That's her first year. She just finished her first year. Her research interest is in SmartNICs, P4 switches, cybersecurity, and robotics. She earned her master's degree in computer communication engineering with focus on mechatronics from the American University of Science and Technology in Beirut, Lebanon. So Samia, I will stop sharing the screen and please share the screen and go over the slides and the lab.
Okay, thank you, Eddie. Let me share my screen here. Okay, so hello everyone, and thank you for attending the workshop. So in this session, I will be going over a hands-on activity in which we will be building a P4-DPDK pipeline for a basic packet forwarding application. So if you are interested in implementing programmable pipelines using P4 and DPDK, this is a good place to start from. I will go over a couple of slides just for you to know what we are gonna be doing in this lab. But before discussing the content of the lab that we are doing, I'm just gonna briefly introduce the P4-DPDK lab series that we have. It's in the cyber training material. You can find it online, and I just posted here the link. So just a second. So you can find the series of labs here collected in one document. So for lab 1, we will be mainly doing that in this lab activity. So it provides a brief introduction about DPDK and specifically P4-DPDK, how they are compatible with each other, how we are going to go from a P4 code to a programmable pipeline that we can run with DPDK applications and libraries. And the P4 architecture being used is going to be the PNA architecture. So the lab series also provides a detailed introduction about the PNA architecture and specifically the building blocks of the P4 code in the PNA architecture. So you can find a lab about parser application, the control block, which includes match action tables in labs 4, 5, and 6, and finally, checksum recalculation and packet deparsing in lab 7. So it's a good lab series to go over. But right now, we are going to be focusing on a general introduction about P4-DPDK. And for us to know what we are going to do in this lab, probably you have seen this figure before, but it really includes all three main programming blocks or main three blocks of the DPDK pipeline. So we have the body of the pipeline, which includes the match action tables. And this is basically where all the logic happens, the packet processing logic happens. And we are also going to be configuring the input and the output ports. So for a packet to enter and to leave the pipeline, we will have to configure these ports as needed in our application. And for us to program this pipeline, there are different approaches, but what we are going to be using, and as it has been previously mentioned how relevant this method is, we are going to be going from P4 to an executable DPDK application. So we are going to start with a P4 code that is going to be available there in this lab. Probably in coming labs, we will go over the process of writing the P4 code in the PNA architecture. But in this introductory lab, the main focus is about compiling this P4 code into the spec file, which is a specifications file that will be taken by the DPDK pipeline libraries. And specifically, we are going to be using here the CLI library to run the specification files, build the C code, and compile it into an executable shared object to run our application. And after we are done with these steps, so first, I'd like you to see here the difference between having a P4 code and the spec file. So we are going to go from P4 to spec file using the P4-DPDK compiler. And if we look at the P4 code, you can see how easier it is to express the logic. So this is a simple apply block where we are just applying simple forwarding. If a port was received at port 0, it's going to be sent to port 1. Otherwise, if a packet was received at port 1, it's being sent back to port 0. Just a simple forwarding application. But if we were to look at how the code is being converted or expressed in spec file. For those of you who are familiar with machine language, low-level language or assembly, you can see the move, for example, function, the jump, the extraction of the headers being expressed here, and also this is the jump if equal. So this is simply when you have an if statement with a condition there where we are checking if comparing two variables, if they are equal to each other. So we'd rather mainly look and put our efforts in writing a P4 code, and the work will just be done using the P4-DPDK compiler. And to test this workflow and bring it to life, we are going to build this lab topology. So we are going to have our P4-DPDK application running on a host, and we are going to be consuming solely the CPU cores of this P4-DPDK host here, as it's labeled. And we are going to have two hosts, host 1 and host 2, connected, and each isolated in a namespace. So we are going to be building this topology and ensure connection between these two hosts. And if the connection has been successful, then the packets are being received through the P4-DPDK, they're entering the pipeline and then they're leaving the pipeline all the way to host 2. So to get started, you will first need to have access, and I'll be posting this in the chat box. So for you to have access to the NetLab platform, you will need to use this URL. You can either use the link in the chat box, or right here in the schedule, you can use the link to, but in my case, since I am on campus at USC, I will have to do that differently. So for your username, you are expected here to enter the email address that you have used to register for this workshop. I'm just going to be using here a test user to display all the steps needed for you to get started. I am just assuming that some of you haven't attended day 1. And the password, it's a temporary password set for everyone, is NSF 2024. You will be asked to reset your password. So definitely if you have used the platform in day 1 and you have already reset your password, you will use your own password. You can change the password here. So I encourage you to do this lab along with me. And if you are having any problems logging in, please let us know in the chat box. Okay, and for you to book a lab reservation, you will have to click on the new lab reservation button right here. It will show you a drop-down menu where you will have to specify that you are scheduling this lab for yourself. And in this lab activity, we are going to be doing the P4-DPDK lab 1. Okay, so I see that some of you have already scheduled a lab there. So to schedule a lab, right now, you will have to click on the red line and specify the time duration for which you will be doing this lab. Okay, so you might have a reservation conflict, just like this one. So probably someone has booked a reservation as I am doing so. So I will have to go through the process again. Okay. Once you can see your lab here on the main screen with the Enter Lab button, you are good to go. So you press on Enter Lab. And to run your VM, you just click on the client. And to have the the lab manual side by side with the VM, I will use the undock button here. Okay. Okay, so you can see the table of contents. The lab provides an introduction about DPDK and P4-DPDK, but I will be skipping all the way to section 2, where we introduce the lab topology. And
Samia, before you
yes,
continue, let's just pause for a minute just to make sure everyone is has their environment loaded up.
sure. So please, if you are facing any problems, we will assist you. Just have to let us know here on the chat. Yeah, we are doing lab 1.
All right, Samia, feel free to continue.
Okay, thank you. So first step would be launching a terminal. And in this terminal, we are going to use the code command, and the code command will load VS Code, but we are going to load VS Code with a specific, within a specific folder that includes all the scripts that we are going to need to build and to run our application here. And that would be the P4-DPDK labs. And then you direct to the lab 1 folder. So that will open the lab 1 directory in VS Code. You will see that we have a bunch of scripts that we are going to go over, but first we are going to inspect the P4 script. I'm not gonna go over it, but it's a simple packet forwarding application. But what we mainly need to see here is that this P4 code was written with the PNA architecture. And this information is important for us to compile the code into the spec file. So in step 3, we are going to open a new terminal by clicking terminal here in the menu bar, and then in the drop-down menu, new terminal. I'm just gonna close this, the Explorer tab, just for you to be able to see here what I am typing. Okay, so after the terminal is loaded, we are going to use the P4-DPDK command, which takes as an input the P4 script and outputs the spec file. And this is why we need to know the architecture, because this command also takes as an input the architecture. We will have to specify the architecture here. So you can go ahead and type in the P4-DPDK command, specify the architecture, --arch. We have used the PNA architecture here. Start by specifying the P4 code we are compiling, lab1.p4, -o to specify the output, lab1.spec. So when you compile, you would usually see in the terminal if any errors were detected or the compiler is facing any problems compiling your code. So in this case, you will have to go back to your P4 code and do the appropriate adjustments so that the spec file will be compiled properly. But if you didn't see any errors, then you are good to go. And if we go back to the file explorer here, we can see that a spec file is added. So this is similar to what I have shown in the slides. So mainly if we go back here, what we have done right now is simply going from the P4 code to the spec file using the P4-DPDK. And what we are yet to do now is to use the DPDK pipeline libraries to do the rest. So in the upcoming step, we will be preparing the P4-DPDK CLI script that you can see here. So we will go ahead and click on lab1.cli. And for you to know what we are going to do in this script right here, we have some commands that will guide you step by step through the lines of codes that we will have to add. So we will first start by specifying the C code, or like typing in a line of code that will take the spec file as an input and that will generate the C code. So that would be the first step, as we have seen here in this in this workflow. So we'll have to use the code gen function, and it goes as such. You'll have to first type in pipeline code gen. So the first argument here would be the path to the spec file. So that's in home, admin, P4-DPDK _ labs. lab1 and lab1.spec. Next, we are going to be writing the line of code that when executed, we will have a shared, first we will have to specify the path in which we are going to deposit the C code. And we are just gonna name it lab1.c and just place it in a temporary repository. So next to build the share object, we are going to be using the lib build function. So you type the second line of code here, and it's pipeline lib build. And the first argument taken here is the C code, and specifically the path to the C code. So temp lab1.c. And the second argument here would be the path in which we are going to keep the shared object file, or which is the executable executable file, which we are going to use to run the pipeline and run our application. So that would be in the also temporary directory lab1.so. Okay. Next, we are going to be listing the DPDK devices used for this application, and whatever is specified here in this, and the parameters being specified here in this step are customized based on your application. And this is basically the where you tune the parameters to fit your application and also to enhance performance. So for our application, we will mainly be using 2 Ethernet devices. So since we have 2 hosts, and we will have like 2 Ethernet interfaces connected to these hosts. And we will be using also a memory pool that will be that will be configured as follows. So we will first start by calling the mempool function, and it first takes the name of your memory pool. We are just going to name it mempool 0. Okay. And it first takes the argument meta, which is the private the private size of the memory buffer, and it's going to be specified in bytes. And this is mainly used for like application specific and private data. So we are not mainly going to use it, so that's why it's going to be set to 0, but we are going to use the packet buffer instead, and we are going to specify the size of this memory here to be 9,128 bytes, and the pool size, which has to be greater than what we have specified for the packet buffer size, is going to be specified as 32 kilobytes. Next, the cache size also in byte is going to be specified as 256 bytes, and that would be that will have to be a power of 2. And finally, we are going to pin this memory address to a NUMA node with the ID 0, and that would be helpful. So we are going to see later also how we are going to pin the pipeline to the same NUMA node, so that the memory will be directly accessed and they will all belong to the same NUMA node. So NUMA 0, we are here specifying the NUMA node ID. It holds the ID 0. Next, we are going to configure our first Ethernet device, fdev. So we are going to use the fdev function. And we are going to tag the first Ethernet device as neptap 0. And what we are assigning here as names to the Ethernet devices, we will have to mainly keep in mind, and we will have to remain consistent with the same naming here. So for the first Ethernet device, we are going to use one receiving queue and one transmitting queue. So RxQ is going to be the flag, after which we specify the number of receiving queues, and then the size of the queue, 128 bytes, and that would be pinned to the mempool object, which we have specified before mempool 0. And the same Ethernet device is going to be also associated with one transmitting queue, TXQ. We are specifying here the number and the size of the queue in bytes. And finally, here we have the promiscuous feature. We are going to set it to on. So as it was mentioned in the previous presentation, DPDK tends to process packets in batches, and that's to increase its performance. But for this application, we are going to be setting promiscuous to on, and this feature will ensure that every packet being received is going to be processed. So the Ethernet device on host 2, on the second host, is going to be tagged as nettap1. We are also going to be using one RxQ. So they're going to have the same features as the ones assigned for the first Ethernet device, nettap0, mempool 0. Same thing for the transmitting queue. We only have one. We can specify here the size and also promiscuous feature set on.
So Samia, just before you continue, these 3 lines that were added here, and actually the whole file, most of the time is gonna remain fixed, so that the focus would be more on the P4 program, right? Now, if you see here, you're seeing a lot of details like the mempool and what are the different values to be assigned to each. If you ever use DPDK, the first thing you would do is create a memory pool too, even when you use C there. So here, really, these are the same parameters that you would need in any DPDK application, but we are expressing them in this CLI file because that's what's going to be fed to the pipeline application so that it can allocate the memory and do all this stuff. Now, a lot of these numbers, most of the time, I mean, if you write them like this, even with those numbers, we got 100 gigabits per second for the heavy hitter detection. You might need to do some more tuning, but that's application dependent. But at this point, it's not very important to understand every single detail of these. So you can just assume that they are there and focus more on the packet processing in P4. Okay,
Yeah.
Continue, Samuel.
So if we move to step 4, we are going to specify here the pipeline that we are building. So we are going to use the pipeline command. We are going to tag our pipeline with a name. We're going to call it here pipeline 0. We're going to use build. And the first argument here is the shared object library. So you type lib, and then you specify the path to the shared object library. So that's in the temporary directory. And then lab1.so. IO, which is the input-output configuration file that we are going to be writing right after we finish the CLI file. So this script will be in this script, we will be configuring the RX and TX ports, the input and the output ports of the pipeline. So this is what we are going to be doing next. And the path to this is the same path that we are using for the spec file and for also the CLI file. So that would be in the home directory, admin, P4-DPDK _ labs, lab 1, and it's called ethdev.io, ethdev.io. And finally, we are going to be pinning the pipeline that we are creating here, pipeline 0, to the same NUMA node used previously. So you type in NUMA with ID 0. Finally, we are going to be enabling this pipeline to one CPU core. So pipeline 0, enable thread 1. So if you have multiple pipelines here running the your application, you might need to pin to associate them with different CPU cores. And finally, don't forget to press enter to have an extra line in there, and then Control S to save.
One more thing before you change the this code. So if you guys have a physical NIC, right? Let's say from Mellanox or whatever, Intel, the only two lines that need to be changed here are line number 7 and 8. So instead of using a tab device, which is the virtual NIC, here the tab is just a software NIC that we are using for education purposes. But if you have a real device, after ethdev, you would write there the PCI address of the NIC. So you can get that information by writing lspci, and then you will get the address from there. It will be something like 0007:00.0, whatever it is. You copy it and you put it here. So that's how the pipeline knows which physical port it's going to be using. But here, because we are using a software NIC, a virtual NIC, we are using a tab device.
Correct.
You can continue.
Okay. So after we're done with this final step here, we are mainly done coding the CLI script. Okay. So we are gonna go ahead and configure the input-output ports, and that will have to be done in the IO ethdev.io file. Okay. So the first thing here to do is to define the pipeline input ports, and to do so, we will have to type in port in, and then ethdev, which takes the name of the Ethernet device that we have created here. So that would be NetTap 0 and NetTap 1 in our case. So first we are going to be configuring NetTap 0. And as we have also specified here, so whatever we do here in the IO script has to mirror the configuration, and it has to match what we have specified here in the CLI script. So you can see that we have decided to associate NetTap 0 with one receiving queue and one transmitting queue. So we are going here to specify the RxQ. The first RxQ would be would hold an ID 0. And what we are going to specify here is the burst size. We are going to set it to 1. So, as I previously mentioned, DPDK will be able to, and is made for such purposes also, to process packets in batches. So it will have to wait until we have the specified number of packets here, until it pulls them to the to the pipeline. So what we are specifying here is that we want to take each packet being received individually. And that's why we have specified the burst size here to be equal to 1. So the next port is also an input port, so port in. And it will have to be associated with the second Ethernet device, NetTap 1. Pin to the receiving queue with ID 0, with a burst size also set equal to 1.
Samia, you forgot to add the numbers. So port in 0.
Yes, sorry. So after we specify that this is an input port, we will have to specify the port ID here, which I forgot.
So these port numbers are basically the logical port. Like in your P4 program, if you want to have a condition on which port this packet is coming from, you write 0 and 1. You won't write the actual interface name like NetTap 0 and NetTap 1. So you'd look at the logical port numbers.
Correct. And then we are going to do the same for the output ports, and to specify that this port being configured here is an output port, we'll have to use port out. And the first port, the output port, will have an ID equal to 0 that is associated to this Ethernet device, which is NetTap 0. And it will be attached to one transmitting queue with the ID 0 and burst size also equal to 1. Finally, to configure the output port of the second interface, so that will be port out 1, and the Ethernet device pinned to this port is going to be NetTap 1. Add the transmitting queue with ID 0, burst size equal to 1.
So in a realistic scenario, you would need to increase the burst size to more than just 1, because this means that the pull mode driver is only pulling 1 packet from the NIC at a time. But to get good performance, maybe you put this as 32 packets, or depends on the traffic profile that you have. But here we just use 1 so that you immediately apply the action on the packet and you see the effect on it just for learning purposes. But if you put it 1 in a real device, you will get low performance. So make sure to increase it to a larger value so that you pull multiple packets at a time.
All right, so don't forget to save. Control S to save. And once we are done with this step, we'll be having all of these 4 scripts ready, and that's all we need to run our P4-DPDK pipeline. So we are gonna go to maximize the terminal window again. Sudo su to enter root mode, and the password is password. And before running the DPDK pipeline, we are going to be reserving large memory blocks called huge pages. And to do so, we are going to have to specify the number of huge pages needed to run the DPDK pipeline. If we miss this step, we won't be able to run the DPDK pipeline. So we'll use echo to write the value 1024 to the following directory, which writes the value being here specified to the number of huge pages. So that's sys kernel. You can use the tab here to autofill the directory. Huge pages, huge page dash 2048K. And finally, nr underscore huge pages to specify the number of huge pages here.
Just a quick comment. So DPDK requires the use of huge pages. And the reason is the idea is not to use the default page that is used by Linux. You need to make it large enough so that you have contiguous memory blocks, right? And this is an essential step as well, so that you don't have a lot of translation misses when you want to translate between the physical address and the logical address. We call them TLB misses, the table look-aside buffer. So the idea here is to minimize as much as possible the misses and then have contiguous memory blocks where your packets will be. But any DPDK application would need the huge pages. Otherwise, it's gonna give you an error when you run the application. Okay, continue.
Correct. Sam. Okay. So we are going to go to the DPDK directory, cd DPDK. And in there, we are going to be running the pipeline. So first, we will have to specify the path to the pipeline executable executable file. So like this executable file is going to be running the DPDK pipeline. So you go ahead and specify examples pipeline build pipeline. Next, we are going to be using the -c parameter here to specify the core mask or the number of cores being reserved to run our DPDK pipeline. So we are going to be reserving 3 cores, and you will always have to reserve 1 extra core, and that extra core is going to be engaged in all pipeline building and execution of the CLI script and some extra functions, and the rest of the reserved CPU cores are going to be like mainly engaged with the packet processing and will be running the pipeline. So
one more thing, Samia, just to correct what you said. We are not using here 3 cores. This is just the core mask, meaning that if you convert this number to binary, you will get the rightmost bit set to 1 and the one next to it set to 1 too, meaning you are using, so if you add those, that will get you 3, meaning you are using 2 CPU cores. Is that correct?
Yes. One will be used for the running the pipeline because we pinned it to 1 CPU thread, and the other would be pinned to for extra like processes, other processes there.
Okay.
Mm-hmm. And we are going here to specify, or this is where we are going to be creating the software next instances by typing --vdev for virtual device. And we are going here to specify the name, and it has to be consistent with what we have set in the CLI script. So we are going to type in here nettap 0 and assign a MAC address of, so this MAC address is going to be ending with 01. Okay. And next we are going to create our second software NIC, also --vdev nettap1. And we are going to be assigning here the MAC address ending with 02. Dash dash, and then the dash s here parameter takes the CLI script or the script that is going to be executed at startup. So S for startup, and that's in home, admin, P4-DPDK labs, lab 1, lab1.cli. Yes, so basically, if you were not using virtual NICs, if you were using regular NICs, you will not have to create virtual devices. So here we are creating and assigning MAC addresses to these virtual devices. All your configuration will be already have been included in your CLI script and in the .io file. Is that
So
clear?
you would omit those --vdev
Yeah.
from this command.
Okay. So running this command will actually run the and execute all of the lines included in the CLI script, and it will actually print out your CLI script here. Okay, so all of the lines being printed here are executed one by one. You will see that the additional lines are are some like feedback. If you have any errors, they will be showed under the line being executed. And if you don't see any additional lines, then your CLI script has been successfully executed. You don't have any errors here. All right, so next, we are going to be inspecting the interfaces of the Ethernet devices or the software NICs that we have just created. So we are going to go to a new tab. And use ifconfig to see the configured Ethernet devices. So you can see that they are named here DTAP0 and DTAP1. So these are the names or like the tags given to these Ethernet devices by the operating system. And any operation that involves the operating system will have to take these names to refer to the interfaces. Whereas, so you can see that the Ethernet, the MAC addresses are the ones that we have specified for nettap 0 and nettap 1. But to access the pipeline, we can type this command telnet 0.0.0.0.8086. So this is like a broadcast IP address and the port. So it will give you access to the pipeline, and we will use the fdev show command, which is part of the pipeline CLI commands, and it will inspect the configured Ethernet devices. And you can see here that we have configured NetTap 0 and assigned it to have the MAC address ending with 01. And as we have specified in the CLI script, it is pinned to one RxQ. So this is the number of RxQs and TXQs. And the port number also specified in the IO file are all shown and displayed here. Same thing for NetTap 1. So for any operation that involves the DPDK pipeline, you will have to refer to these interfaces with these name tags here, NetTap 0 and NetTap 1. Now we can exit the pipeline by pressing Ctrl and close bracket, and then type the word quit. Finally, we are going to be building our lab topology. So that's, we are going to use sudo su to go to root mode. Password is password. So we are going to be creating the lab topology shown here. We'll be creating namespace H1, namespace H2, pinning them or linking them to these Ethernet devices, and we are going to be using DTAP 0 and DTAP 1 because these operations here involve the operating system. So that's how we are going to refer to them, and we are going to assign finally IP addresses to them. So we're gonna start by creating the first. So netns is the command used, ipnetns, for network namespaces. So that's what we are going to use to create the namespaces. netns add h1. Same thing for h2, ipnetns add h2. Next, we are going to be attaching them to the interfaces DTAP 0 and DTAP 1, respectively. IP link set DTAP 0 netns h1. So now DTAP 0 is going to be part of the h1 namespace, and IP link set DTAP 1, which is going to be attached to the second namespace H2. Now we are going to be turning the interfaces up. And now since DTAP 0 and DTAP 1 are now like an entity of the namespaces H1 and H2, then the following commands have to be executed in the namespace. And to do so, we will have to use IP netns exec H1. So whatever follows is going to be executed in H1. IP link set dev DTAP 0 up.
You have a typo
Sorry,
on the last one.
Mhm.
Samia, let's try to wrap it in the next 5 minutes because we're out of time and it's the break time now.
All
So
right.
let's try to
Almost
complete
done.
it. Okay.
So we're gonna do the same for H2. Next, we'll be assigning IP addresses. And same thing here, these commands will have to be executed within the namespaces. ifconfig DTAP 0, and we're gonna assign the IP address 192.168.10.1. with subnet 24. And to execute another command in H2, we'll have to do the following. And the command to be executed in H2 is ifconfig dtap1 192.168.10.2. Also it's subnet 24. Okay. And now we are going to be adding static ARP entries to establish connection between the two hosts. -s for static, and 192.168.10.2, which is the IP address of the second interface, is associated with the MAC address ending with 02. Okay. And here we are also adding a static ARP entry in host 2, where we are associating the IP address 192.168.10.1 to the MAC address ending with 01. Okay. Now the topology is built, and we can ping H2 from H1. So we will have to execute the ping command in H1. So that will take the IP address of host 2. And we're going to do this for 4 times. So we can see that the connection is clear between these two hosts. And if we go back to the pipeline, we can see that we have some logs that mainly identify the commands being, or like the process being executed to process these packets. So we can see that first we have extracted the headers, and then we have, so this is while parsing, and then we are deparsing the packets, and then a packet has been sent to port 0, and the packet has been received back to port 1, and that's basically the dynamics of the packets being sent from one host to another and being received back through the ping command. And to stop the pipeline, you're just gonna Control C here. And that's it. Since these two hosts are able to communicate together, and so these packets are being processed by the pipeline, and we can see here the logs that describe how the packets have been processed in the pipeline. So if you have any questions, or if you are facing any problems, please let me know in the chat box.
All right, thank you, Samia. Yes, please, if you have any question, please let us know. We're 5-6 minutes past the time, so now if we go back to the agenda, we have a break, and then after that we're gonna come back to the second day of the workshop, and we're gonna discuss the portable NIC architecture, and then we will do another lab, but this one is going to be about the P4 program. So what Samia showed was just to run the pipeline. We assume that the P4 code is already there. In this next one, we're going to show how you can write the P4 code. So with these two labs, you should be able to get started and then deploy it.
Yeah, Eli, we will keep it the Zoom open. So this will be open. Otherwise, is if you get out of the meeting and then you want to come back, it's the same URL. So just that clarification.
Yes, thank you.
Right, thank you everyone, and we will be back at 3 p.m. Eastern time. Welcome back everyone. We will continue the last portion of our workshop, and we have a guest, Andy Fingerhead from Cisco. He will be talking about portable NIC architecture. Then we will have a lab on match action tables. That will be by Ali Masloum. He's a PhD student here at the University of South Carolina. And that will conclude our workshop. So I will let Eli move forward from here. Eli, do you want to share your screen and introduce Andy?
Sure, thank you. Thank you, Dr. Jorge. The next speaker is Andy Fingerhut from Cisco. Andy has been involved in the P4 language community since 2017 and has since served as a co-chair of the P4 architecture working group with regular contributions and discussions with the P4 language design and API groups. Andy and his co-chair, Canon Cascaval, wrote well over half of the P4's portable switch architecture specification, and probably the PNA too, but I will let Andy correct me after that. He hasn't kept count, but has probably created over 100 issues over the years in the open source P4 code repositories on GitHub. Andy's been very helpful for everyone in the P4 community, actually. He maintains a public repository that has a lot of guides if you want to install the P4 compiler, all the tools that you might need, as well as example codes. He's been very helpful for us too when we build those labs. We asked him a lot of questions and he was very responsive and helped us a lot. So thank you, Andy, for joining. I will stop sharing my screen and you can share yours.
Great, thanks. All right, slides visible again?
Yes, we can see it.
Right. Howdy, everybody. My name's Andy. As said, I have a little bit of background, but I think it doesn't overlap much except for the last line with in case it, so I thought I'd throw some things up. I actually got a doctorate in computer science in a past life in 1993. Weirdly enough, after doing theory of algorithms, I spent 5 years doing ASIC design while doing a research project there. And I think that's actually been quite helpful in my career. I've always been close to the hardware-software boundary of working on systems since then. And I've done a lot of stuff with programmable data planes of, whether the language you use to program is P4 or assembly language or C. There's a lot of programmable data planes out there, and I've worked on several of them. I've been at a couple of computer networking startups. Fortunate enough that actually both were bought by Cisco Systems, and I've left Cisco 3 times and returned to three times so far. That probably won't make that 5 or 6, but maybe 4. I don't know. We'll see. And I was at Intel for most recently since about 2020, but recently went back to Cisco. And yeah, the P4 stuff I've been involved with pretty heavily. I'd encourage you to stop me and ask questions anytime. My slides are a little, tend to be wordy and not very picturey. And I think the best value for you is if you have any questions, please speak up and let me know. So just a little bit of background. I don't know how much everyone knows about P4 and P4 architectures, but just sort of, some basic, I'll go quickly over some of the background here. In 2014, when Barefoot Networks was getting started and they decided they wanted to make a public language to program it, a publicly specified language to program it, they published a P4-14 specification. They formed a P4.org as a public separate organization, separate from the company Barefoot Networks. They published the P4-14 specification, and it defined both a programming language and, in the same specification, how packets flowed through one kind of network switch. And I copied a figure from that old specification, which probably at the high level of, packet arrives from a port at the input, goes through a parser, goes through some match action tables, goes into a queuing or buffering system, and then there's egress match in action as we flow from left to right, and then the output port. That high-level view is pretty common across all the architectures I'll mention that involve switch architectures, at least. It also defined in that spec where and how you would drop, mirror, multicast, resubmit, or recirculate packets. If you're not familiar with all those terms, don't worry, but basically like all the things that don't go from left to right in this figure or duplicate packets or get rid of them are defined in that spec as well. So the P4-14 spec combined both of these things, the language and this sort of switch architecture. Before I became involved in P4, which was early 2017, they had almost finished the P4-16 specification. The language, the syntax changed quite a bit to be more, C, Java-like, more familiar from other programming languages. But they also realized that if they wanted this programming language to be, they would limit its usefulness if they included this sort of switch architecture in it. And so rather than sort of baking those or combining those together in one spec, they said, well, let's define a way to define what we will call a P4 architecture. And we'll give an example called very simple switch in the language specification. But any more serious, non-toy example will be defined in a separate specification later, separate from the language specification, and can evolve independently of the language. And so they chose to do that then. And basically the motivations were, even among switch architectures, they might not all look like this, ingress, traffic manager, egress, programmable egress. They might just have ingress, for example. Many switch architectures have been like that in hardware in the past. And, programmable NICs in the future, might look quite different. I'll pause there. Any questions that I might have missed? Feel free to speak up if. So I'll keep going. So I'm going to do a really quick mention of a few switch architectures before I talk about the portable NIC architecture. Some of you might have heard of the V1 model architecture. This was officially sort of the first architecture for the public one from P4.org. It was primarily intended as a way to do automatic translation from P4-14 programs into P4-16 programs, which was important. Early on in P4-16's life, there were a lot more P4-14 programs than P4-16, so having a way to auto-translate them was helpful. And so this V1 model architecture was basically a P4-16 architecture that worked like the P4-14 architecture. No one ever wrote down a specification document for it, and it's effectively defined by its implementation in open source. I've written some detailed articles describing it, but they're basically just following from my learning of what the implementation does in that open source. Moving on quickly here, I then worked on, became the co-chair of the organization. We were working on a portable switch architecture. And so this was the first architecture published by P4.org. Most of the work was done in 2018, 2019 timeframe, and there haven't been a lot of big changes since then, mainly it's minor touch-ups. And the main differences from the V1 model architecture were it explicitly has an ingress deparser. So V1 model doesn't have an ingress deparser, and it doesn't have an egress parser, whereas PSA does. And I think there's some like murky corner cases of like mirroring packets and things like that that are actually hard to describe precisely what happens in all cases. I'm not even sure I know without going back and looking at the C code that implements it, like what happens because of the lack of these things. It also turns out that Tofino physically has these in its hardware, and it's sometimes useful to take advantage of explicitly programming what they do as opposed to hiding them from the user, from the programmer. The PSA also tries to be much more explicit. Like it's not defined by a C implementation in C. We try to define it in English and precise pseudocode in the specification. But other than that, it's very similar to V1 model. And the packet flows are not. There's no new ones that didn't exist before. And then there's the Tofino native architecture, which I actually also worked on the document that became the public document that was published in the Open Tofino repository. And it's defined by Barefoot Networks and Intel later when Intel acquired Barefoot. It also has an ingress deparser and egress parser. Again, the hardware does, and it exposing them to the developer explicitly sometimes is helpful for taking advantage of that hardware. There's a lot of small and large differences with the portable switch architecture. I'll just mention a couple. Well, one, implemented a real product. That's a pretty big, a real ASIC that you can buy and use. Some more detailed examples. There's something called a direct register extern, a register being an array of elements that you can, in P4 source code, read it, an entry, have a programmable update, calculate a new value to write back, and then write it back into the same entry while you're processing a packet. It's useful for a lot of stateful features, and TNA defines this. The PSA architecture didn't define it, but it lets you have sort of one-to-one programmable state in a table per table entry in a table. And then, the multicast replication features in the traffic manager of Dofino are a lot fancier than any published specification I know of. Things for like layer 2, layer 3 combined, layer 2 and IP multicast combined together in the same packets are easier to do with TNA than with anything else that I'm aware of. Let me pause there for any questions. I'll switch over to Nick's from the rest of the talk here. But any questions about that so far? Okay, so I joined Intel in 2020. That was the part of the company that was Barefoot Networks. It was acquired in 2019. I never was part of Barefoot Networks, but I joined Intel and was in that part of the company working with those people. At the time, Intel was well already underway in the progress of making what is now known as the Intel IPU, very highly programmable data plane, programmable NIC. And two of the first assignments I was given at Intel in 2020 were to work with Intel's P4 compiler team and advise them on how to represent what the hardware could do in P4 source code in a way that was sort of familiar to P4 developers. And with the constraint, the tricky part often was in a way that the P4 compiler team could then, not have to do new programming compiler research to figure out how to translate that source code into something that they could run on the hardware. So those constraints are often tricky to meet, but and then also to work with engineers from other companies and start up a effort to define a portable NIC architecture spec that would be published by P4.org. So that effort actually started in 2020. It's maybe for various reasons that I'll talk about. It hasn't gone as smoothly as I originally hoped it might, but there are good reasons for that hopefully will make sense. An early question, of course, was, shouldn't we just look at the portable switch architecture and just figure out how to compile that and run on a programmable NIC? Some high-level things that were so differences between NICs and switches. Many differences, but even from the view of, P4 source code and what kind of features you can write that you want to write to run a programmable NIC and take advantage of its hardware that don't tend to come up very often for programmable switches or any Ethernet switches. In some cases, there are very few of them. One is, half of the I/O bandwidth of the device is a PCI Express interface to the host, not Ethernet. And there are Ethernet ports as well, but half of your packets go to or come from the host, typically. And then also, besides the expected packet paths of packets coming from the host, going to the NIC and out the Ethernet port, and vice versa, the opposite direction. While you might think that's the common case for NIC, and it is for many NIC deployments, there are a lot of people that often want to deploy them so that packets go from the host to the NIC and back to the host, or from an Ethernet port to the NIC and then back out another Ethernet port without ever going to the host, never crossing the PCI interface. So those are common things that we want to be able to support well and expose the P4 developer and make it easy for them to do. Some of the features that are very rare on switches but common on NICs are you want to do TCP or UDP payload checksum offload. Doing full payload checksums on a switch ASIC is very rare. Usually you just want to check the IP header checksum. And if the full payload TCP or UDP checksum is wrong, the switch just forwards it on and expects the receiving host to figure that out and drop it. it's just expensive to do it to touch every byte that way in a host, in a switch ASIC, extra cost. Encryption, full payload encryption and decryption in the fast path is much more common on NICs than on, I mean, it does exist in some switch ASICs, but it's a rarer feature, certainly, and very much more common in NICs. Highly stateful features like TCP connection tracking, I'll talk a little bit more about, with many different variations. Segmentation reassembly features like large receive offload and TCP segmentation offload, extremely common. That's sort of like bread and butter for NIC. So you don't want to leave those out of cables out of programmable NIC, and many flavors of remote DMA. So these are some of the main reasons why we thought, that, and also just the packet flows. So there's been many different variations of this picture. This is the current one from the portable NIC architecture specification that we've arrived at after more hours of discussion than that you might expect. So on the left, we have the network ports, typically Ethernet. On the right, we have something that's, I'll talk a little bit more, mention later, called message processing, but also the host PCI interface on the right. And then in the middle, we've got a single programmable pipeline. There's no ingress and egress split like we see in the earlier architectures. But there is, this familiar parser, control, and deparser sequence. And then there's the accelerators afterwards. And so packets coming from, whether they come from the network interface or from the host, go to this common pipeline. And then the pipeline can choose where they go next, either recirculating through the loopback path you see, or going to the network port or the host afterwards. There's a simple, there's a defined send to port extern function in the specification, PNA specification, with a destination port ID. And basically, not only are there destination port ID values for numbering the Ethernet ports, but they're also so-called vPort or virtual port IDs that can number one of many logical destinations on the host. For example, some deployments you might want to have one vPort ID per virtual machine running on the host, or you might want to have many vPort IDs for representing separate queues, potentially on per virtual machine, and other possibilities. I'll pause there for any questions.
Yes, Andy. I wrote in the chat window.
Okay.
Do current smart NICs, as far as you know, conform with this PNA model? We're aware that Intel has already one IPU in the market, AMD's pensando, etc.
Yep. So I am, while I was working at Intel, which was until last December, I was really focused on the Intel IPU and, wasn't looking carefully at things like Pensando and NVIDIA's Bluefield and other programmable NICs. So most of my knowledge of the other ones was based upon the discussion of, their response to proposals in the PNA specification and what they said, was easy or hard for them to support. So I don't have I'll talk a little bit more explicitly later about what I think the impact of PNA on vendors is likely to be. And maybe after that, if you have any follow-up questions, you can ask then, if that's all right. I do have a little bit to say about that, and but it's not as much as you might like. I don't know. I don't know as much as you might like to hear about that topic, but I can say a little bit about it later.
Thank you. Sounds good.
Yeah. Any others right now?
Andy, I think just one question. When you mentioned the vPort, like a port on the host, right? What type of ports do you typically use there? Like, let's say these are virtual machines. How do you add a port so that you can send a packet from the network to the host or to the VM?
Yeah, so the PNA specification really focuses heavily on the data plane and how you access certain features from P4 source code. Easily, 10 times more of your system complexity and development effort will be in control plane code for configuring these things. And So the P&A specification doesn't say much about that. And I would expect in general, so for example, Intel, the plan was there would be, control plane APIs for creating and destroying vports at runtime. Be up to, for example, that control plane software within, install actions with send to port, actions that invoke send to port with an action parameter of the destination port ID. So the P4 code wouldn't know the vports or make them up at packet processing time. It would get them from the control plane table entries added as action parameters.
Understand. Thanks.
Sure. All right, let me go on a little bit more and then I'll. So as I mentioned earlier, port to NIC to port is a common case. And so the P&A specification, makes that fairly easy to do from a P4 program. You receive the packet. There's metadata defined to tell you which port or vport the packet arrived on. There'd be a common number space that Ethernet ports and vports are in, and a simple Boolean, function that returns a Boolean value. Is this from an Ethernet port or is this from a vport from the host? And then send to port can work commonly. By which number you give it, it will direct the packet to an Ethernet port or the host. And so basically, even if you receive the packet from an Ethernet port, you can do send to port on an Ethernet port, and the packet will follow a flow like on this red curved line shown here. And similarly, if you got it from the host, you can send it back to the host if you want, or recirculate it. This is just a simple example of and you might wonder, like, why do people care about port to port or host to host? The main examples I've heard are things like for port to port, if you want to deploy a programmable NIC as like a network service that's shared by many hosts. So for example, there's the Microsoft Dash project that they plan to sort of deploy a network device out in the network that can do various kinds of tunneling and network policy enforcement on source and destination, 5-tuple classification with fancy group-based classification to permit or deny packets between hosts, and it's deployed sort of as a network service out there as opposed to being locally right there in the NIC in that host. And so deploying that there's no reason to go across the PCI interface if the point is just to do some processing in the packet and send it onto another Ethernet port. And so that some deployments, there might not be even a CPU complex over there sending and receiving packets. It might just be the left half side of this figure only physically. And then for host to NIC and back, maybe there's some offloads like encryption or decryption that might actually be faster if you send it out to the NIC, have it do the encryption or decryption, and then send it back to the host is one example I've heard. Encryption support. So this accelerators box that you see in the picture that I haven't mentioned yet, or maybe I have, would typically include encryption and decryption capabilities on the full payload of the packet. That's a P4 program selected portion of the packet, typically from a certain header onwards to the end of the packet would be the common case. So the flow here would be, packets arrive to the pipeline, the parser parses whatever headers it can see. If it's got IPsec encryption, for example, it can only parse the ones that are in the clear, typically up to what's called ESP, encapsulation security payload header, and everything after that is encrypted, so it can't parse that. And then the main control would do some lookups, table clips, and decide this protocol is ESP, and the source and destination, I'll look up the source and destination address, and maybe a field from the ESP header called spy in a table, and see, should I decrypt this packet or not? And if so, it would assign values to some metadata fields saying, here's the starting point of the encryption. I want to use this decryption key. Here's the part I want to start. And then it would send it to the accelerator, and your P4 code is now done for this pass. And you'd send it to the accelerator, it would perform the decryption and authentication as well. Then maybe the authentication check fails. And typically you would configure it to recirculate the packet after decryption, because you want to come back and you want to see, well, did it succeed? The authentication check succeed. And you probably now want to look at, parse more headers that are in the now decrypted, and you can now see what they are and parse them and do additional processing on the now decrypted portion of the packet to decide where it should go next. So there's an optional recirculate the packet after the encrypt or decrypt operation is done. Any questions on that? I've left out a lot of details, of course, but that's the basic.
One question, I know it's not part of the P&A architecture, but the control plane of the IPsec in this case, did you see it that it's being implemented on the CPU cores of the NIC or on the host, especially those that have CPU cores, the smart NICs, the newer ones?
So in several smart NICs, there are specialized ASIC gates for payload encryption, decryption. On several of them. I'm not claiming that's universal, but I mean, it's enough work per packet and per byte that, the general idea of, the reason why switch ASICs exist, like the reason why programmable NICs and switch ASICs exist is not because CPUs can't do them, right? It's because while you could do them with general purpose CPUs, the price, power, and performance ratios are terrible compared to switch ASICs and programmable NICs. So, I mean, it's a little bit belittling sometimes when I think of this, maybe, but like, most of my work in developing programmable NICs and switches is not because you can't do them on a general purpose, it's because it's way cheaper and less power to do them per packet on these devices. And so doing specialized gates for things is usually the way to get the best price, power, performance ratios. And if it's for something you want to do in every packet align rate, doing it in a general purpose CPU is often a bad choice for those price, power, performance characteristics. So,
okay, thanks.
But yeah, they certainly can be done in, ARM cores or whatever, but that's really a vendor choice. I'll say a little bit about TCP connection tracking as one of the motivating examples for PNA. Differences in PNA versus earlier P4 architectures. So one simple variation of TCP connection tracking is, as TCP packets arrive from the host, you look up the 5-tuple of the packet, source, destination address, protocol, source port, des port, in an exact match table to see, have I seen packets in this TCP flow before? If it's a brand new one you haven't seen before, you'd like to start tracking information about it, or at least the fact that you've seen it before. So, for example, let's say a packet comes out from the network, maybe you want to drop packets that don't match. If you reverse the SADA and reverse the source port and des port, when the packet comes back from the Ethernet port, you like it to match before you allow it into the device. Is one simple reason for TCP connection tracking. So you could, in existing P4 architectures, say, I got a miss in this table, punt the packet to the control CPU and have it add an entry so the future packets match. That's certainly possible. It is functionally correct. It will do it at some rate of new connections per second, but a common desire in these devices is to be able to do that at millions of connection adds per second, not just, tens of thousands. Punting the control plane CPU and then having it do it tens or maybe hundreds of thousands per second is not too hard to achieve, but millions per second is pretty hard to sustain in that kind of path. So having many switch ASICs have had so-called add-on miss capability that you do in the data plane, you do a lookup, you get a miss, and if you get a miss, you decide, I'm immediately going to add a new entry that will match future packets with that key and give it an action to do on those future packets. This has actually been done on like layer 2 learning bridges, layered Mac learning. Have many chips in the past have implemented add-on miss capability in the fast path in hardware for decades. Maybe it's gotten less common, I think, in the last 10 years for switch ASICs to do that because the learning rates for layer 2 Mac learning make it a lot cheaper to do the add-on miss via the control plane punt routine and have the control plane do it, and that's fast enough for Mac learning. But for TCP connection tracking, that the sustained add rates at millions per second really make it easier if you do it in the data plane, or possible, I would say. So the add-on miss was one of the first, successes, I'd say, of the PNA spec definition that we defined how to do this in P4 source code, and vendors agreed, yes, we can see how, we can implement that in our device, and we put some restrictions on it that made it easier to implement in the common case. For example, the common case being the only thing you're allowed to add as an entry in the table in the P4 source code is the key that you just looked up and missed. You can't pick an arbitrary key. You can only do it in exact match tables. The action parameter you get to pick, but the restrictions on the key and the exact match table make it much easier to implement than if you don't have those restrictions. And that's the common case that many features need. They don't need more general capability than that in a lot of cases. Any questions on that? So there are fancier variations of that simple TCP connection tracking. For example, one thing that's commonly cited as a desire to be able to do. So TCP connection tracking is like, I would say, a family of related features. It's not just one, there's not just one way of doing it. There's N ways of doing it. One additional more complex variation, the one I just described, would be every time you process a packet and you hit in that table, that 5-tuple table, you'd like to record in the entry per flow the last sequence number you saw in that direction, like even separately for the two different directions of TCP data flow. And you like to do that independently per flow for millions of flows in the table. And you like to drop packets that are whose sequence number is not in an expected range, like not in the receiver's window, for example, like not in the last sequence number, minimum last sequence number up to last sequence number plus a window size. It would be the range that would be common, or maybe a little bit larger than that. So we looked at ways of, define that just in the architecture itself, but it turns out that there's an extension to the P4 language itself, and it's pretty simple when you see it. I mean, if you're familiar with P4 actions, you can have, one or more action parameter, 0 or more action parameters to an action, and typically those are provided by the control plane when the table entry is added, and they're read only from the data plane. You can't modify them. Only the control plane can choose what their values are. But if you just have a little annotation or an extra keyword in front of an action parameter that says this can be updated in the data plane, this parameter can be. Now, like today, before this extension, if you try to assign to an action parameter a variable name, the parameter name inside the action body, it says compile time error. You can't do that. With this extra keyword in front of it, you could assign it, and the effect would be after the action is executed, all those updated values get written back into the table entry, and they'll be available the next time you match in the entry to see what those updated values are. So that's a very natural way to write code that can implement features like this. There's something called a direct register extern in the Tofino native architecture that actually gives you a very similar capability. It's just a little more clunky syntax-wise to do it, but it's not a brand new feature in any programmable data plane. It's more of just a nicer way to specify it and write it in the language. It's pretty easy for developers to understand. So let's see, how am I doing in time? I'll make sure I don't go too long here. Yeah, pretty short here. Okay, so I'll try to wrap it up quick and leave a little bit of time for questions. So in this process, I mean, one thing I've learned, and I've been told this long before this by somebody who knows well, and I just finally gradually came to believe them. It's much easier to define like a native architecture for one specific vendor's device than it is to try to come up with a common one that works across many devices. And one reason is data plane programmers care a lot about performance. One extra recirculation, if for example, you took a common P4 source code and you compile it for two different vendors' devices, and it took an extra recirculation on this one and not on that one because maybe the compiler was better or the code was just more suited to that device than that one somehow. That's often a deal breaker. Like, you'd want to go in and tweak your program and avoid that. Because price, power, performance matters so much. That's why you're buying these devices, especially if you're a network operator buying many tens of thousands of them. And price, power, performance does matter. So that makes it's difficult to come up with a common subset that works for everybody. So even if no vendor implements exactly what the published PNA specification says in the end, I think there's still some benefits of going through the effort. I think there are a subset of new features like encryption, decryption, like this add-on miss thing, like this modifying parameters in the data plane, specifying the source of that. I think we found resonate with multiple vendors and like, oh yeah, they say that looks like a good thing, and we think we can do at least a subset of that. So in some cases, I think we can make things similar in the source code that if vendors didn't talk to each other would end up different for needless reasons. And another would be, maybe less useful is there's some common terminology that can be used in documentation, even if the implementations or the features are different. And also, if there's an open source implementation of these features, people, who want to try things out without spending a lot of money, just have a laptop, can try these things out and learn some things and practice and use them. And hopefully a lot of that will translate over when they use if they later use a real physical device. even if they need to learn new things, you know, and they typically will need to learn new things when they switch over to a vendor's device. Okay, I won't talk about this last one. I'll leave a little bit of time for questions if we have any.
So, Andy, I have just one question about the add and miss feature. So you mentioned that we can track millions of flows actively per second.
Many devices can do that, yes.
Yeah, so is there any penalty if we have millions of entries at the SmartNIC itself?
So I'll just say, like, the PNA specification doesn't define performance characteristics and those kind of things. It's mainly, you know, functionality, and then it's up to vendors to specify what their performance characteristics are. But I know, so most SmartNICs, unlike most switch ASICs, most SmartNICs have external DRAM chips sitting next to them on the board so that they can have gigabytes of DRAM. And so the main performance penalty is you therefore typically have an on-chip cache in front of that DRAM, and if you get a cache hit, it's really fast, and if you get a cache miss, there's a cache miss penalty, and the latency and or, you know, if you get many, if mostly you get cache misses, it'll slow down your packet processing rate. If you get occasional ones, the latency of some packets will be longer because of the cache miss. So, you know, if you really care about performance to that detail, the expectation is, you know, try it on a particular vendor's device and measure the performance for yourself, because it could vary from vendor to vendor.
Okay, thank you.
They're definitely working hard to make it good, you know, good enough performance.
Yeah.
Oh, go ahead.
Oh, no, just thank you.
Andy, I think I have another question. I think in one of the slides you mentioned RDMA. So how do you see RDMA fitting in the PNA architecture?
Yeah, that's something thanks for reminding me. I forgot that there's this shaded message processing box over here that I didn't talk about that I said I would, and I'll talk about it now. So this is something that's not defined in the PNA specification at all today, other than this box and the description of. So there's been some detailed proposals, especially from Pensando, on basically there'd be some hardware here between the host and this. So this P4 programmable pipeline is sort of a packet by packet. You know, the P4 code receives a packet, does something to it, and then just sends it on its way or drops it. The message processing will also be, I mean, it'll receive packets, you know, one at a time from over here, but the expectation is this would be a very stateful processing part of the device, for example, that might say, oh, I've got a table that has I've just received a TCP packet. Have I recently received a TCP packet with the next lower sequence number that I want to glom this packet and append it to that before I send it over to the host? So that's large receiver offload is a name for that, feature that. Or for RDMA, segmentation reassembly, like it's very common for applications to say, I want to send the 16 megabytes of data, and it's up to the NIC to break that up into packets and send it across the network. And so this message processing block would be, the idea is, you know, there'd be a P4 programmable thing, maybe a very different style of P4 that you've used for the packet processing part. They would be very aware of you know, state between packets, or, you know, receiving pointers or descriptors to 16 megabyte chunks of data in the host memory and saying, now I want to create a packet for the first 8 kilobytes, now for the second 8 kilobytes, now for the third 8 kilobytes. And so this message processing part is intended to, by some vendors, especially Pensando, I think, to be able to have a programmable way to define new RDMA segmentation reassembly protocols, potentially, after the device has been finished and made.
I see. Thank you.
That's that's a teaser, but yeah, there's a lot more detail worked out there.
Yeah, it looks interesting for sure. I think Sarabi, you had the question. I will let you unmute yourself if you want to ask.
Yes, thank you so much. So I have a quick question regarding, like, so I know you talk about ASICs and how we can, you know, use the PNA. So my question is on the FPGAs, like the U2AD, have you, like, do you have any recommendation how we can consider the PNA on these kind of FPGAs?
So in general for, I mean, because I said, you know, it's much easier for a vendor to create a native architecture than it is to create a common one that works across multiple vendors. I expect for a long time, like I say, PNA might define a useful subset that people then build on and add to. So in general, I'd recommend, and I haven't talked to a lot of vendors to find out what do they add, and what do they remove, and what do they change. So for a while, it's going to be the case that if you really care about deploying on a physical device, it is very important to talk to that vendor, get their documentation, see if they have any training classes that are focused on their device, because there will be many significant differences between devices for years to come. So that's not much of an answer other than check with your vendor, really is the short version of that answer. And I don't have any, and I haven't used FPGA program, FPGA, P4 programmable FPGA devices myself personally to know any recommendations to which ones to check in preference to others.
There's a question, Andy, in the chat if you want to answer that.
Okay, let's see if I can find the chat window. Let me, there we go, chat button, good. Let's see, is it from Nishant?
Mm-hmm.
Okay. Is it possible to get line rate performance using PNA due to byte touching for operations? So again, performance is a thing that, you know, vendors are very concerned with, because I mean, you won't buy their device if they don't achieve the performance you want, and another, especially if another vendor's device does. So one of the reasons why, yeah, payload, so both payload checksum calculation as well as encryption are things that, you know, if someone wants to provide that at line rate, and I think most of them, I think TCP payload checksum offload at line rate is like, if you don't have that, you're probably nobody's going to buy that NIC as a NIC. So I think this is something that, because vendors care about selling devices, this will be very commonly done at line rate by whatever mechanism they choose.
I have a question.
Yep.
So for the remote direct memory access, does the PNA specify like any specific interface? Because there are a lot of like security attacks on RDMA. Is that something taken into consideration?
So the PNA specification, unfortunately, if you were to read it, is unfortunately because of this difficulty of finding a common set of things to specify. It leaves out a lot of things that I think a vendor's full capabilities will specify. In particular, the message processing thing that I talked about for segmentation reassembly, and that would probably have the biggest thing to do with how you would secure RDMA protocols, is not specified at all in the PNA specification. There's been some live meetings where proposal been discussed in the architecture work group, but nothing's been written down except in some slides presented so far. I would say if you cared about what capabilities are available there, you know, if you have access, if you have, you know, access to a Pensando device and or training or documentation, ask them, or ask somebody, you know, NVIDIA Bluefield. You know, if you have vendor documentation, that's going to give you a better answer to that question today than the PNA. The PS specification will not answer that question for you today.
Thank you.
One other question: do I expect smart NIC vendors to implement multiple P4 pipelines per NIC, as the case for Tivino? Yes, someday, when the total bandwidth through a NIC is large enough that it is difficult. I mean, the main reason to have multiple pipelines in Tivino and any other chip is 1 packet per clock cycle through a pipeline is about the maximum, like 2. It's much easier to develop 2 pipelines that are copies of a 1 packet per clock cycle throughput pipeline than it is to develop 1 pipeline that's 2 packets per clock cycle. And so basically it depends on the clock cycle and the packet rate you want to achieve, whether you want to have more than 1 physical pipeline. It's always convenient for the programmer to have 1, but because as soon as you have 2, you typically have independent state often between them that you have to keep track of for some features, stateful features. So yeah, I expect when the packet rates get high enough on a programmable NIC that it's hard to do 1 pipeline, they'll go to 2 or more. But I think that might still be a few years off before they end up doing that. That's my guess. It's still right to call P4 as platform independent, since, as you mentioned, the market is driving. So, I mean, the fact that it's a common syntax and semantics of the language, even though they have different, external functions you can call. I agree that that does hurt portability. Actually, maybe I can flash up a slide, my last slide that I didn't talk about before, and just like, oops, yeah, here we go. If you can see that, hopefully. So I know some people worry about, having, it's certainly the case for C programs. Like, when's the last time you thought about portability of a C program, except for, as long as you got the right if-defs in there and you're on a supported platform, usually it just works out of the box. But for example, like, have you ever tried to compile MySQL on a microcontroller with 64 kilobytes of RAM? I'm pretty sure it's going to fail. So there are constraints even on C code of, portability, limiting portability. It's just when you're working on laptops of today and server class machines, you rarely hit those kind of limitations of memory. But in P4, you're closer to the hardware. You care more about achieving the maximum out of the device you can possibly get. Again, that's why you're buying the device, that category device. And so you hit the limits more often. And so for people that worry about, let's say, vendor lock-in, like if I can't take the same P4 program and just compile it without changes on 2 different vendors' devices, don't I get locked in to one vendor or another? And my answer to that is, like, if you're a manager at a company that you're going to be deploying tens of thousands of these devices, you're going to have a pretty decent team of people, writing control plane code. In this slide here, a large P4 program, not the largest, but a large one, is 10,000 lines of code. Not teensy, but not huge. A small control plane program is 100,000 lines of code, in my experience. Now, my experience is Cisco mostly, so maybe that's a little bit skewed by the features sets, but 100K is like 1 million is what my original estimate is. But even if you have a more focused feature set, 100,000 lines of control plane code, that's where most of the complexity of these systems is. So if you're hiring a team to develop control plane code and P4 code, and you want to support 2 or 3 devices with different styles of P4 code, like, I would say, get 2 or 3 people to focus on one vendor's device P4 style and another one to focus on another one, and still 90% of your team is going to be writing control plane code and debugging that. So as long as with those small groups of people working on those vendor-specific devices implement something by talking to each other that the control plane developers don't have to care which of those 2 devices it is, it's okay if P4 10,000 lines of P4 program are different 10,000 lines of code, as long as your 100,000 lines of code are the same. Economically, that makes good sense, I think, for such a person. So I think even if it hurts portability, I think there are reasonable approaches to dealing with that. And I think, until these price, power, performance issues are, had some time to mature, I think we're going to have noticeable differences for a while, just because there is no standard that everybody feels locked, that implementers feel like they must implement or else people won't buy them. Anyway, that's my guess.
Andy,
Yep.
Can you talk a little bit about the open source backends for P4C and or what backends support TNA? I know DPDK does, because we are doing some hands-on session now. After this presentation, there's one on match action table, and actually we're going to show how to do the add-on miss as part of the lab. But what about other backends like TC and eBPF, XDP, these kind of stuff?
So there is a Google Summer of Code project. P4.org has had 4 students participate in Google Summer of Code for P4.org projects for the first time this summer. And one of them is working on additions to the BMV2 or behavioral model software switch to add PNA features. That process, I mean, it's a fairly big task to modify both the P4 compiler and behavioral model to do this. And so it certainly hasn't come to a point where I'd say it's ready, go off and use it, but they've made some progress. And somebody might pick that up after the project is done at the end of the summer. But to my knowledge, DPDK is the most feature complete PNA implementation that I know of in open source. I haven't looked at P4TC enough to know where it is feature-wise.
I see.
It's mainly a thing of, yeah, I mean, vendors focus more on their proprietary implementations than an open source one. And so it really is up to, mostly hobby time or people that are interested more so than the P4 compiler has gotten a lot more participation in like on the front and mid-end code, not back-end dependent. So the backends for most P4 compilers are completely proprietary. The non-open source ones, though, for real, targets tend to be closed source proprietary, whereas the front and mid end are common, and people that work on the back end tend to help add features to the front and mid end. But when it comes to software switches, like, it's really kind of a hobby project for most people, not a something they're paid to do, to contribute to open source anyway today.
Yeah, and I see, I mean, a lot of updates and additions to the P4C, at least in the front end.
Right.
I mean, if you see the GitHub, it's like on a daily basis, you see updates.
In the last 6 months, there's been about 2 or 3 developers from AMD and 1 or 2 from NVIDIA that have joined active development on the P4C front and mid end. And that's as recently as 6 months ago. Like, before that, it was really like mostly one person doing over half the commits.
Yeah,
so
I wonder if
so that's good news for the longevity of the project and the interest that there's this interest among multiple companies to help enhance it. That's
yeah,
great.
I wonder if NVIDIA would start supporting P4 for their Bluefield. I think I read a paper somewhere that
I believe their plan is to do so, or if not, they're spending way more time in P4 projects than would be reasonable. I don't know officially what their support plan is.
Gotcha.
It might be
All right.
Bluefield 3, where they start more support than with the earlier versions, perhaps.
Yeah, I think so too. All right, is there any other questions for Andy? Anyone?
Great. Well, thanks for having me, and I'll send you my slides, Ellie, after the meeting. And I think the bio you have is pretty good, but I also have one of the first slides. So, but thanks for the opportunity for talking to everybody here, and feel free to join us on P4 Zulip if you have any P4 related questions, and I and other people will see them there, and other ways to participate online too, of course.
Yes, thank you so much, Andy. We will upload the slides online, and yes, I will also post the link to the Zulip channel and other p4.org resources that could be of help for everyone here. But thank you again. This was very useful. And we're going to proceed now with the next lab, which is basically a continuation of what we did from the first lab. But we're going to be looking at how we can implement a match action table. I just want to confirm, are you seeing my screen?
Yes.
All right. So the next presenter is Ali Mazloum. So just introduce Ali very briefly. So Ali is a PhD student in the College of Engineering and Computing at USC. He's working in P4 Tofino. He also worked in Perf Sonar. He developed some plugins to the latest Perf Sonar. And yesterday he showed in the demo. So he's been actively working in P4 and different projects around that, from performance measurements to cybersecurity. He has a bachelor in computer science from the American University of Beirut. And he will be presenting the last lab for today, match action tables. So in this lab, you're going to see many of the things that were discussed in the PNA presentation. So match action tables, add-on miss, all of these fun features. So Ali, I will let you share your screen and proceed from here.
Thank you, Eli. So let me share my screen first. Can you see my screen?
Yes.
Okay, good. Let me just move this one. So thank you everyone for attending the meeting. And as Eli mentioned, now I'll be giving the lab on match action tables in P4. So this lab that I'll be giving is from the P4-DPDK lab series. It's lab 4. Again, it's about match action tables. And before starting the lab, I'll give one slide brief about the lab that includes the topology. So this lab, the topology we are following is similar to the lab before the break. We have 2 namespaces connected through a P4-DPDK pipeline. The aim of this lab is to implement match action tables inside the pipeline so that there's connectivity between the 2 namespaces. But we have multiple scenarios. The first scenario will focus on implementing the exact matching tables. So we'll be exactly matching on the destination IP address of the packets to decide on the forwarding action. This will be the first scenario. After that, we'll focus on implementing the add-on miss feature. And to the best of my knowledge, this is mainly in PNA architecture, where, as Andy mentioned, at the data plane directly without the contribution of the control plane, we can add entries to the tables that can be also deleted automatically by the data plane after a specific time, and this is known as self-expiry timers. We define those while we are setting up the configuration for the add-on miss functions, as we'll see soon in the lab. So at this stage, let's just have a reservation. So I believe Samia showed you the steps, but once again, the lab is part of P4-DPDK labs, this lab series. It's lab 4. So we should have reservation there. And as I see, you already have some reservations. Just click on the red line, extend the time a little bit, and have a reservation.
Ali, let's wait a couple of minutes just to make sure everyone
Yes,
is
sure.
able to log in and have a reservation.
Yeah. Anyone, please, if you have any errors, problems logging in or having reservation, let us know. We can help you. So, can you still see my screen?
Yes, we can see the NetLab with the client.
Okay, great.
All right, Ali, you can continue.
Okay, so once you have a reservation, you can click on content just to have access to the material, the manual. I will undock it. And by clicking on the client, you will have access to the virtual machine. So let's undock this one too and put them side by side. And it's here. So let me zoom in a little bit. So let's skip the introduction, go directly to the lab topology. So the first step we'll be doing is implementing exact matching. For this, we should first start by loading the programming environment. For today's lab, we'll be using Visual Studio Code as a text editor. So let's start by starting a terminal. Here I'll zoom out a little bit so we can see everything and use the command code, the path to the directory, which is P4-DPDK labs, lab 4. I'm here, step 2. So this will start a Visual Studio Code instance. Now click on the control.p4. This file will contain the logic of our P4 program. We'll be defining the actions, the tables, and the apply block. So I will minimize the panel here just to have more visibility.
Ali, just one second before you continue. I think it would be a good idea to show them all the different parts of the P4 program, because in the first lab, we just used the P4 program there, but we did not inspect other parts. So can you go over the parser and the other files?
Okay. So the first file we should consider is the headers. Usually we define, we have type definitions, constant, and the header structures for our protocols and so on. This is inside the header function. After that, we have our parser. This file will contain the parser implementation, where we'll be parsing the header, extracting the fields, and so on. After that, we'll have a pre-control block. So it also might contain some processing logic. For our lab, we'll not be using it. We'll be using the main controller, this one. So the pre-controller and the main controller, both files contain processing logic. We can process the header fields and metadata we extracted from the packets. And finally, we have the deep parser. This file is responsible for emitting the headers or combining back the headers we extracted and the payload, serializing them and forwarding them through specific egress. The egress to be forwarded from, and so everything is defined inside the main block based on the actions we are taking. So yeah, these are the main control blocks of the PNA architecture. Now let's go back to our manual and start implementing the actions that we'll be using. The first action is forward. So this action will be responsible for forwarding packets through a specific port. The syntax is simple, just action, the action name, and now we define any parameters it might take. So here it will be taking port ID. So port ID is the port at which we want to forward the packet from. This function itself calls another primitive function. It's defined by the language. It's send to port. And this one, send to port function, it takes port ID and forwards the packet through that specific port. So this is the first action we'll be defining. Moving forward, we'll define another action. So the other action is drop. This action will be responsible for dropping the packets. And this action, similar to the forward action, will be invoking another primitive action, drop packet. Once the action drop packet is invoked, the packet will be immediately dropped. No further processing will occur to that specific packet. So at this stage, we have two actions, one action to forward the packet, one action to drop the packet. Next, we should define a table. So to apply actions, mainly we use tables. And tables, they have keys to match on. And here, because we are using exact matching, we're using exact matching on the destination address of the packets, will be defining a single key, but we might have multiple keys. So to define a table, we start by table and then the name of the table. Then we should specify the keys of the table. So what are the header fields or metadata that we use to match on? And here we'll be using the header.ipv4.destination address. Address exact. So this one, exact, means that the matching type is exact. In P4, we have different exact matching types. So key equal. We have multiple matching types. We have exact, we have LPM, we have ternary. We can, each one has its own use cases, but for now, for this specific lab, we'll be using exact matching on the destination IP address of the packets. So after defining the key, we should define the list of actions that this table forwarding can apply. And we'll be applying the two actions, forward and drop, or give the table access to these two actions. So here at step 7, we define actions to be the forward and the drop actions. So here, please note that we are not applying the actions. Yes, we are just defining the table. The control plane will be responsible for adding rules to this table, populating the table, at least for the first scenario for the exact matching. So the table forwarding, we define the matching key, the list of actions, and we can define also the size of the table. So the size of the table represents the number of entries this table can hold. And here, when we say the size is 1024, we mean that this table forwarding, accepts at most 1024 entries or rules. The control plane can populate up to 1024 entries. So the table forwarding is defined. The actions are defined. Now we should define the apply block. Apply block, inside the apply block, we define the list of, or the sequence of actions to be performed by our application. So here, because we are forwarding packets based on the destination IP address, first we should verify that the IPv4 header exists. And when we say header.ipv4.is valid, what's happening here explicitly or in the background is that we are checking if the parser extracted the header IPv4 and depopulated it, because the parser is responsible for extracting the headers, unpacking the packet and extracting the headers. So when we say header.ipv4.is valid, we are checking whether the parser or not extracted that header. So if the packet extracted the IPv4 header, then we can apply the forwarding table. In this case, we say forwarding.apply. Now, in case the IPv4 header is not valid, the parser did not parse this header, or the packet did not contain this header, we'll be just dropping the packet, and we're using the drop action. So at this stage, what we did, we defined two actions, one action to forward, another one to drop. We defined a table that match exactly on the destination IP address of the packets, and it accepts two actions, drop and forward. And then we applied, inside the apply block, we check whether the IPv4 header is valid, and we apply the forwarding table. Otherwise, we drop the packet.
Let's just
Yeah.
pause a little bit, Ali, and if you can go a little bit slower just to make sure everyone can follow. Can you elaborate a little bit more on the IPv4 is valid condition? So
yeah,
when does this condition become true?
So I'll just go a little bit to the parser and show them how the parser works. That will make it easier for us to understand what is valid means. So once the packet arrives, the first thing we check whether, or start by the state. This is a default state that directly transition to parse Ethernet state. So here we extract the Ethernet header and check if the packet or if the ether type is parse IPv4, or let me open the headers too. So headers and parser, have everything open for us. So here, when we say type IPv4, this type we already defined here in this file, and it stands for 0x0800. If the Ethernet type is equivalent to this value, then the packet has IP version 4 header, and we parse IPv4. If that's the case, then the .isValid function will return true, because we parsed IPv4 here. We extracted something to IPv4. Otherwise, if the ether type is not this one, then we'll directly accept the packet, but the IPv4 header will not be valid. So isValid will return false. If we go back to the control plan.p4, what we are saying here, if the parser detected IPv4 header and extracted it, then we should have access to the destination IP address, because it's part of the IPv4 header. Then we can apply the forwarding table. Otherwise, the parser did not have access or did not find the IPv4 header. The packet did not have the IPv4 header and will be dropping that packet. So any question regarding the logic inside the apply block or any other aspect of the code?
One comment, Ali, I think you have a typo in forwarding. Just make sure in the apply block it's correct so that it doesn't give you an error. And yeah, so always in P4, you will go to the apply block. This is the starting point. If you think of a C function, C program, that's the main function, right? And from there, it's invoking those tables and actions that you defined previously. As Ali was saying, so first you define the action, the tables that you want, and then in the apply, this is where you start executing those. So you define your logic there. So is valid, as we said, this is an implicit function. It's automatically created, right, for all the headers. So at any time, if you want to check if your packet is or has TCP headers, or if it is UDP or IPv4, whatever it is, you can use this as valid function. And how would it know if it has TCP or UDP or IPv4? Is what Ali was saying. So in the parser, if it extracted the header for that specific protocol, like TCP or IPv4, then isValid will evaluate to true. Okay. All right, you can continue. Thank you, Ali.
Yeah, thank you, Uli, for the elaboration. After adding this, we just press Ctrl S to save the changes and compile the application. So for compilation, we'll be using the terminal from Visual Studio Code. That one can be accessed from here. So if you click on terminal here, new terminal will have a new terminal and will be compiling the application or will be creating the .spec file. So to do that, we'll be using P4-DPDK. The architecture is PNA. The source P4 code is main.p4. And the output is the .spec file. So the .spec file, this one, the specification file, will be used later by the pipeline library to build the DPDK application or to run the DPDK application. If we have no errors, we should be able to compile. So hopefully we have no errors. Moving forward, we'll be building the P4 DPDK pipeline and the lab topology. So first, let's go back to the Linux terminal. We initiated at the start of that lab. Type sudo su to have root access. And for the password, we use password usually for our labs. So for password, just type password. Next, navigate to the directory where we have lab 4. So cd p4-dpdk/lab 4. Now we are inside lab 4. What we'll be doing to run the pipeline, we'll be using the function run pipeline.sh. So the step-by-step process of running the pipeline, Samia described in first lab. Here, we are just automating the process by running this script. To have more data about the process of running the lab, I urge you to go back to lab 1. But for here, we're just using this script. So run pipeline will take care of everything for us. Now, let's just focus on this one in this specific line. So we are loading rules to the match action tables. What that means is that in the data plane, when we define the table, we just define the matching key and the action, the list of actions that that table can use. But we did not define any entries. The control plane is responsible for adding entries to tables. And here we are already adding some entries or rules to the table forwarding by using the add command and specifying the path to the file rules.txt. So the file rules.txt contains the rules added to the table forwarding. Will be we'll see what that file contains soon. So to do that, first we'll have another terminal. create another terminal by clicking on the plus sign, top left corner. Here, we need root access, so sudo su. Just make sure the manual and what I'm doing are aligned. So sudo su for password, as before, is password. Next, we'll go to the directory where we have the lab 4. So cd P4-DPDK labs lab 4. And here we have the file rules.txt, the one that we use to load the rules. So to dump its content, use cat, and then the name of the file. It allows you to see what that file contains. And the file rules.txt contains 2 rules. So we'll start by the first rule. What we are saying here is that the rule, it's matching on this IP address, but it's in hexadecimal format. If we want to translate it to IP address, it would be 192.168.10.1, or the IP address of host H1. So the first to match on this destination IP address, what action to be applied is forward. So apply action forward if a match is occurred on this destination IP address, and give action data 0x0 to the forward action. So when we define the action forward, we gave it one parameter, which is the port ID. And here we are saying that if a match occurred on 192.168.10.1, apply action forward with port ID 01. Or in other words, all packets with destination address 192.168.10.1, forward them through port 0. Any
Ali,
question regarding this?
You might want to show the P4 code on the right-hand side. No, like show both the rules and the code so that they can understand.
Okay. So I believe we have, I'll just go use the manual.
Yeah.
It'll be easier for us. Okay, it's upward a little bit. Yeah, here. So this is the P4 code, and this is the action forward. So the action forward accepts port ID as input. And based on port ID, it will be forwarding the packet. So when are we invoking the action is inside the table. So if we go back to the table forwarding, here, this table, it matches on the destination IP address. That's why here, when we say match, we should provide IP address, but we are using the hexadecimal notation. So we specify what is the matching key, which is this one, the key. After that, we should specify what action to take, which is forward. Here we have 2 actions, but we are saying if we match on this specific IP address, then apply this specific action forward. Now, because action forward accepts one parameter, or the port ID, we specify it here as the action data for that action. So again, to summarize what I said, if a match, exact matching occurred on this specific IP address, which is 192.168.10.1, apply action forward and use action data 01, or forward the packet through port 0. Any question about this one? Okay. So for the second rule, we are following the same approach, but now we are saying that try to match on this IP address. This is another rule, so we should have another destination IP address. This one, if translated to IP address, it will be 192.168.10.2, or the IP address of host H2. So now we are matching on the IP address of host 2. If there's a match here, then apply the action forward, but this time use action data 0x1, or the destination port should be 1. So when a packet arrives with destination address 192.168.10.2, forward it through a port 1. So these are the two rules we are having that have exact matching on the destination IP address, and we'll see them in action soon in the next few steps. So let's go back. And we are here we run edit another terminal here. So now we'll start the topology. The script.set topology, this one will create two namespaces for us. Both of them are connected through the P4-DPDK pipeline to just automate the full process. We just have to run it. And the testing will be as follows. We'll be sending one packet from host H1 to host H2, and then we'll inspect the logs at the P4-DPDK application to see what happened in the data plane. So to do that, because it's a namespace, we should use IPNet NS, execute, followed by the name of the namespace or H1. Now we should define the command to run at the namespace H1. The command is python3 sender.py. So we'll be running the script sender.py. This script accepts two parameters. First, the source, or from where we are sending the packet. So it's we are sending it from H1. And second, the destination IP address, which will be the IP address of hosts H2 or 192.168.10.2. So now one packet was sent. We are sending it from H1 toward H2. We are expecting that it should be forwarded through port 1 because it will be matching the second rule we defined. So if we go back to the P4-DPDK pipeline and inspect the logs, we see that first 3 headers were extracted: the Ethernet header, the IPv4 header, and the TCP header. Because the IPv4 header was extracted, it's a valid header, and we'll be applying the table forwarding. And here you can see that the table is being applied and it has a hit. So table forwarding has a hit and action 1 was performed, or the forward action is performed. And because the destination IP address of the packet we just sent is 192.168.10.2, that egress port should be port 1. That's why here you can see after emitting the headers by the deparser, the packet was forwarded through port 1. Any question about what happened here?
So let me just add one more thing, Ali. If you are planning to test P4-DPDK on a physical NIC, you will not be able to see those logs. But because we are using the virtual NIC and we enabled logging when we compile the DPDK, we are able to see pretty much, the life cycle of that packet when it enters to the pipeline. And that's very useful, especially when you're writing a large P4 program, just to be able to understand what's really happening there. Here, it's a little bit simple because you only have one table, but if you want to add a lot of features, the program can get more complex and it becomes a little bit hard to, see if a specific condition is being executed or evaluated to true or not. And this is one of the challenging things in P4. So it's not like C where you can write printf and then you know where you are there. Everything is happening within the pipeline, right? It's hard to find out where you are there. But by enabling logging, you should see that information and would help you troubleshoot your program. What else? So Ali, you showed the rules, right? The TXT file.
Yes.
Okay. So with that, this is something that, the control plane would populate. Okay. Very similar to if you have like a legacy switch or router and you populate the tables manually. This is what we are doing here. In the data plane, we are defining what the table would do, but then in the control plane, we are doing the population of these entries. Okay. But next, we will see that it's also possible to use the data plane to add entries to the table. So I just want to mention that. Ali, you can continue.
Okay. So let's stop the pipeline because we'll be editing it and adding another features. And start by the process of enabling add-on miss. The first thing is that we have to navigate back to the Visual Studio Code where we are editing the code. Next, we'll go to headers. So I already opened header, but in case you want to navigate to the headers file from the panel to the left, just to choose headers and it open for you. Just minimize this again for visibility. And when we are defining add-on miss or enabling add-on miss, there are a few things we should define first. The first thing is the time expiry profile ID, or how long should the entry we just added or the data plane added should survive before being removed by the data plane itself. And we'll see this in action, but for now, let's define it. To do that, I'll be copy pasting this one. So we're defining new time profile ID. Call it expire time profile ID. We'll be using the ID of value 4, but we should first cast it to expire time profile ID data type. So after defining the expire time profile ID we'll be using with the entries, we should define the action data we'll be giving to that entry. So add-on miss, what it really does is that inside a table, it will add entry associated with a specific action. And in our case, it will be the action forward. But because action forward accepts some parameters, we should define them inside struct and then giving them to the action inside the control block. But for now, we'll be defining the structure that will hold the action data for the action forward once we are adding the entry, or once we are using the functionality add-on miss. So at this stage, we are just defining some data types and structures. We did not use them so far. And again, because forward action keys will be used with the action forward, it will have a single variable inside of type profile port ID. So we defined expire time profile ID. We defined the struct forward action keys. Now we should use them inside the control plane, inside the control block. For this, just type Ctrl S or press Ctrl S to save the changes and navigate back to the control. Inside the control, the first thing we'll be adding is a new action, the action forward miss. I'll explain in details this one after I type it here. Okay, let me maximize this one here. So we defined a new action, forward miss, and the main thing will be invoked inside forward miss is the add entry primitive action. So add entry, this specific action is the one that the data plane will use to add entry to a specific table. How it works is that it accepts action. So when I'm adding an entry, with which specific action should I associate it? Because as you saw in the rules file, when you are adding entry, you should specify the action to be performed after a match occurs. And here it's the same. So the entry added should call a specific action. And here we are using forward, the specific one. Now, what are the parameters that should we pass to the action forward after it's invoked by this specific entry? They are specified by the parameter action params, and it's a structure. That's why we define the forward parameter structure, and we initialize the port ID to be 1. Here we are saying that once a miss occurred, just call the forward action with port ID 1 on that specific destination IP that we missed. And the third parameter is the expire time profile ID, or the time to live of the added entry. So after we are adding entries, if no hits occurs to the specific entries for the time defined by the profile ID, just remove that entry, delete it from the table. So this is the forward miss. And now after we define it, we should add it to the apply block inside the table forwarding. And we're doing that next. So let's go to the table forwarding, and here we'll be replacing the forward, the drop action we used before with the forward miss. So forward miss is one of the action specified or that forwarding table has access to. After that, we should enable the add on miss feature. So you should manually enable this feature for each table you want to enable this feature to. And to do that, after the size, in case you specify the size, you just say add on miss and set it to true. Now the table forwarding has add on miss feature enabled, but enabling the add on miss requires you to define default action. It's the action that will be applied once we have a miss. And inside this action, actually it's the forward miss action. One thing here to note, which is very important, the default action used when you enable add on miss should always include the add entry primitive action. Otherwise, it will not work. So here what's happening inside the forwarding table, if a hit occurs on this IP address, on the destination IP address, the action forward will be applied. Otherwise, if there's a miss, we'll be calling the forward miss action here as the default action. Inside the forward miss, we'll be adding entry to the table forwarding with the IP address we just missed. So we at the most miss the IP address once. After that, we directly add entry for that IP address. And for the added entry, we'll be calling the function forward with action data port ID 1. So now the table forwarding was defined, or the things added to table forward. Next, we'll be compiling back the application. But before doing that, do you have any question regarding what we did so far? Okay. So we'll just compile the application the same way we did before, using P4-DPDK, specifying the architecture to be PNA, giving the source P4 code, and specifying the output specification file. Okay, if it compiles, then you have no typos. It's working. Next, we'll be repeating the same steps as before to run the pipeline and so on. So navigate back to the terminal, Linux terminal here, and issue command run pipeline.sh. Again, this pipeline, this script will automatically, or will automate the process of running the P4-DPDK pipeline. Did I save? Okay, I did not save the changes here. So make sure to save that change to the control plane. And now compile again. So let's just stop the pipeline and running it again. So the reason that I knew that I did not save the file is this one. So before, when we tried to add or populate the table for wording from the control plane, that it was successful. But now we have this error, invalid entry in file rules.txt. The reason this happens because the table now for P4-DPDK pipeline is it's not a normal table, it's a learner. Because add-on miss feature is enabled, you can no more manually populate the table. It will populate itself at runtime. The data plane will be responsible for that. If you try to add entry from the control plane, you will have the APIs will be complaining and you have this error, invalid entry in that specific file. So the pipeline is running. It's saying this error does not mean that the pipeline is not trying, it's running. Next, we'll go to here. And now, if you remember here, inside the headers file, I told you that we defined expire time profile ID. But this ID, it does not directly represent the expiry time in seconds. It's just a profile ID, and depending on the target will map this ID to the specific number of seconds. For us, we can see profile ID that's matched or mapped to 300 seconds by inspecting the files lab4.spec. So if you use cat lab4.spec, you will see the content of this file. And inside the timeout section here, this one, you will see the list of expiry ID, time expiry IDs. And because we used profile ID 4 and start counting from 0, it's 0, 1, 2, 3, 4. It's 300 seconds. All the times here are in seconds, or the profiles will be mapped to times in seconds. So profile ID 4, it's mapped to 300 seconds. This means that once an entry is added by the data plane, it has 300 seconds after the last hit. Otherwise, it will be deleted. So if no hits occurred for 300 seconds, the data plane will automatically delete that entry. And you can specify different profile IDs. Now we'll run the topology. So inside the Linux terminal, set topology. And we repeat the same experiment as before. So from host H1, we'll be sending one packet with destination address of host H2. IPNet NS execute. This one is necessary because we are using namespaces. After this, there's the name of the namespace, Python 3, the script sender.py. The source of the packet will be H1, and the destination will be the IP address of host H2, so 192.168.10.2. So before we send the packet, we are expecting that a miss will occur because the table or learner forwarding has no entries at all. Once it observes a new packet, it will miss. After that, it will populate a new rule. So once we send this packet, if we navigate back to the pipeline, you can see that we extracted the headers and we have learner here, and it has a miss. So the miss occurred because we have no entries inside the table. No entries means once we observe new packet, it should be a hit. And after a hit occurs, because we enable the add on miss, we know that a new entry is added to the learner forwarding. So if we now send another packet, the learner should automatically already know what to do with this packet. It will automatically populate a new rule at runtime. So if we press enter a few times, send another packet, there should be a hit now, a hit because the entry was automatically added. So send the packet, go back to the P4-DPDK pipeline, inspect the learner, And yes, we have a hit. The data plane automatically populated the learner forwarding. And here you can see that the exit port is 1 because the action we defined or inside the control block here, the exit port we defined by our action forward miss is 1. That's why here you can see that the first time it was 0, the default one, but now the exit port is 1. As long as 300 seconds did not pass on the last hit, as many packets as we send will be always hit. And this should conclude our lab if I did not miss anything. Yes. So this concludes the current lab, the lab on match action tables. Please let me know if you have any questions.
Thank you, Ali.
Thank you.
I don't see any questions yet. So for those who are interested in this lab library, what else is covered in the library?
Yeah, so let me go to here. So this lab library contains 7 labs, starting from the basics, how to configure everything in P4-DPDK, and then moving forward, we'll be discussing the main blocks of PNA, P4 PNA architecture. We'll be describing the parser, describing the match action tables, and the parser. After that, we'll be focusing on each specific block. So in lab 3, we have a full lab on the parser only, how to define states, how to parse different headers, and so on. Labs 4 and 5, they will focus on match action tables. So now I did lab 4. It was about exact matching and add-on miss feature. Lab 5 will also be about match action tables, but will be describing LPM matching, more advanced matching capabilities. Moving forward, we'll be populating and managing match action tables at runtime. So in lab 4, what we did is that we already configured the rules.txt file. We already included the rules, but in lab 6, the learner will be adding the rules from the control plane to the data plane. So you will be manually populating the rules at the from the control plane. And the final lab will be about checksum recalculation and packet deparsing, the last 2 controlling blocks of the PNA architecture. So this is the lab library already defined.
Okay. Yeah, I don't see any questions. So let me go back to the program. Well, thank you very much, Ali, for this presentation.
Thank you, Dr.
So this is the last activity of this 2-day workshop, where this technology is a pretty new portable NIC architecture. So we only developed 1 library so far, but if you are interested in this technology, we will have more workshops on this and more libraries, including libraries with actual physical NICs. Eli, I don't know if you want to briefly talk about what is in the roadmap regarding network interface cards libraries.
Yeah, sure. So this introductory library was just using the virtual NICs. However, I mean, we didn't test the performance, but if you try to use something like a throughput test, you will see that you won't get that much performance, maybe 50, 100 megabits per second. So we will be developing another library where the same topics are there. You will learn all the topics on PNA and P4-DPDK, but using a physical NIC. So you should be able then to see high performance, like 100 gigabits per second of packet processing. That's something that we are planning to do. And the other thing is we're finalizing another library on P4-DPDK that specifically focuses on cybersecurity applications. So if you're interested in deploying maybe like let's say like a SYN flood detection and mitigation program using DPDK or using P4-DPDK, it will show you step by step how to do it. DNS amplification, slow DDoS attack, heavy hitters, all of these different topics will have their own libraries.
Yeah, I think there is a comment there. Jacob, I'm not a network engineer, but think this is really great technology. How can we at institution make use of these tools to have better performance on our networks, especially these dedicated to research computing? I don't know, Eli, if you want to talk, or well, I will briefly talk about that, and then I will let Eli to add. So all the technologies that we cover here, we make available to let me just call the community CI community, cyber infrastructure community. So the virtual lab libraries, certainly these are virtual, but we plan to do physical. If you would like to use this technology in your campus, one way could be, for example, purchasing the smart NICs, and we will be developing code for smart NICs, for physical smart NICs. That's something that is going to happen. And learn how to program these smart NICs, and the code will be available. It's going to be open. So that would be one way. As an example, we are deploying in our Science DMZ technology that incorporate P4 switches, and the code is open. So building on what is being done already. So that's one way. Eli, that you are the one who is leading this smart NIC. Do you want to mention what is what type of code we might have available in the near future for smart NICs?
Yeah, sure. I mean, basically what you said, Dr. Jorge, and in addition, I mean, we plan to make everything open source. So the systems that we're gonna be deploying, whether they are through part of the labs or part of our research, can be available. And the nice thing about this DPDK and P4-DPDK is that you don't have a lot of changes or really any changes, even if you have different NICs from different vendors, right? So whether you get it from NVIDIA or Intel, that's the same P4 code that you will write there. And that's something that makes it easy to port programs, right? Portability is enhanced. We're also going to be developing some more advanced topics like on network measurements. If you want to do more precise measurement and have telemetry collection, this is some application that we find very attractive for networks. So that's something that we're going to be also working on in the future. And one other thing is we're planning to develop these libraries as well on Fabric, the testbed that we shared today and the first day of the workshop. And there, basically, you will have access to physical NICs that you'll be able to run all of these experiments, and you can test your system in a real network with real propagation delays between the different sites. So you can do like a large scale kind of experiments. So all of these are part of the roadmap, and we should have some new updates by the end of the year, and next year, probably a couple of more lab libraries will be available.
Thank you, Ali. I will share again my screen with the program. I don't see any other questions. So all the material is in the website of the workshop. So the recording will be posted here, the number 2 recording. So expect that by the end of the day or by tomorrow. PowerPoint slides will be here as well. Most of them are already here. And the last thing that we we would like to ask is if you have a few minutes to complete the survey. We try to improve always based on the input of the attendees. So your input is important for us. So if you can take a few minutes for the survey. Thank you, everyone. I don't see any questions, so this will conclude. I don't know if Jason is here. I know that Jason was busy, or Jennifer, the co-organizers.
Yeah, I was able to just join, Jorge.
Excellent. Just on time, Jason. So we are finalizing the workshop. We finished all the activities. Anything else that you want to add?
No, I just think we thank everybody for being able to participate. And certainly if people have questions after the fact, we're always happy to help, whether it be jumping on the phone to try to explain something or to offer anybody any additional assistance that they may need.
Excellent. Well, thank you, everyone. This concludes our workshop. Have a good rest of the day and the week.